with my collaborator listed here, the member of Tohoku University, and Jasri, Riken, Ehime University, and KIT Germany as listed here. So first, I would like to briefly introduce our research topic, high pressure earth science, and how the inelastic X-ray scattering sound velocity measurement contribute to it. So the internal structure of Earth is one of the most important research topics in earth science. And the most reliable information about the Earth's internal is the preliminary reference Earth model called PREM, the seismic model of Earth's internal based on the seismic observation. So the PREM provides a sound velocity and density profiles corresponding to the depth of the Earth. And by comparing this seismic model with the high pressure laboratory experiment result, then the structure of the Earth's internal has been discussed. So since pure iron alone cannot account for this seismic model PREM, based on the large effort of previous high pressure experimental work. So the material of the core, Earth's core, is considered to be iron nickel alloy with some light elements. So the candidate for light element are, for example, silicon, sulfur, oxygen, carbon, hydrogen, and etc. However, which elements are in the core and how much is still being debated. So for the discussion of the core through comparing with PREM and laboratory experiment, precise measurement of, for example, phase relations and density at high pressure and high temperature condition, and also sound velocity of iron and its compound or its alloy under high pressure and high temperature conditions are required. So density information at high pressure can be obtained from compressional experiment. For example, Hirao et al. 2022 recently reported the experiment for iron and nickel compression experiment at up to 370 gigapascals. On the other hand, sound velocity measurements are still under development, and most discussions are based on the extrapolations from 100 to 150 gigapascal result. However, further experiments at higher pressures are needed for more detailed discussions. So, method for directory measurement of sound velocity includes, for example, ultrasonic measurement or Boolean scattering measurement. But these methods have issues such as experimental difficulty at high extreme pressure condition due to sample thickness or etc. Or in the first place, Boolean scattering, the inability to measure the transparent material, so such as metals. On the other hand, the inelastic X-ray scattering method observed phonon dispersion in samples with X-rays directly and is therefore well suited for measurement the sound velocity of metals under extreme pressure conditions. So our study was performed at Springway, a third-generation synchrotron radiation facility located in Harima Science Garden City, Japan. which has 8 giga electron volt to electron beam as its light source. And Spring 8 is now planned to be upgraded to its fourth generations, aiming to increase the brightness of its synchrotron radiation by approximately 100 times, and is scheduled to be in operation in financial year 2029. Well, this photo is the Spring 8 photo. Our experiment were performed at the BL43LXU beamline of the Riken Spring 8 Center using a diamond anvil cell, which is a high pressure generator. So this photo is a panoramic view of BL43LXU beamline and their staff. So right person is Dr. Alfred Red Baron, and left person is Dr. Alfred Baron, and right person is Dr. Ishikawa-san on the right side. So we put the sample. Here is the sample stage, so we put our sample on here, and we get the AfLS contribution by using this analyzer. So there is a very long distance to measurement. So the AfLS spectra were measured by total 28 4 times 7, 28 analyzer. The crystals. And the X-ray diffraction, powder X-ray diffraction pattern were measured by the flat panel, both installed at BL43 LXU beamline. Also, under extreme pressure conditions, the inelastic X-ray scattering contributions becomes very weak due to several factors. So in order to reduce the scattering background and improve the signal to noise ratio, we developed the newly designed called solar screen was used for the measurement. So the inelastic X-ray scattering contribution is generally very weaker than that of the elastic scattering under high pressure. But if when we use the solar screen, specially designed for the high pressure experiment, made it possible to identify this weak AfLS intensity that will be otherwise too obscured by background before. So this red is without solar screen profile. Blue is with solar screen profile. So we can see the weak, we can identify the weak AfLS contributions by using this solar screen system. Asymmetric diamond anvil cell with a 30 to 20, 200 micrometer accurate diamond anvils were used to generate high pressures, and compact system for generating extreme pressures and temperatures system, a portable laser heating system, which is now operated on BL43 LXU beamline, was used to generate high temperature conditions. This inset, this is a photo of compact system, and this inset photo shows the actual heating sample in the diamond anvils. Sorry for very small photo, but brighter area is laser heated area. So today I would like to introduce our three topics for our recent IXS work. So first, I present the result of a sound velocity measurement for hexagonal cross-backed HCP iron under pressures conditions exceeding the core pressures of 300 gigapascals. So one of the improvements in this study is the sorry, improvement in this study is the improvement of the diamond anvil shape. In this study, high pressure experiments were performed by using a newly designed diamond anvil, we called step beveled, similar type of toroidal anvils. As first, we used the general, to be honestly, as first we used the general double beveled type anvil, and succeeded in generating pressure above 300 gigapascal. But the diamond cracked within 1 to 12 hours after starting the IXS measurement, and all experiment runs failed into too many diamonds. With too many diamonds were wasted. Therefore, in order to keep the pressure stable for long experimental time, for example, half a day or 1 day, or we improve the diamond anvil shape into this stepped shape, in collaboration with GRC of Ehime University, Dr. Sakai. This improvement made it possible to keep the pressure above 300 gigapascal for our IXS measurement of long exposure time, above 1 or 2 days. So here I present our IXS measurement result. So this figure shows a typical example of the IXS profile of HCP iron at above 300 gigapascal. So these blue peaks are longitudinal acoustic mode of iron, and these orange peaks are transverse acoustic mode of diamond. And this large green peaks are longitudinal acoustic mode of diamond. This figure plot all observed excitation energies and momentum transfers of HCP iron at each pressure. So their sound velocity is derived from the relation of this sign equation between excitation energy and momentum transfer Q and sound velocity. So the VP of iron approached in such higher pressures, the contribution of VP of iron approached to the contribution of VS of diamond. So, as shown, as I marked here, these peaks almost overlap. So, the experimental limit in principle in when the VP of iron is equal to the VS of diamond. But in practical, although there is still appears to be a difference in this dispersion curve, but as you can see, both peaks almost overlap, so making it difficult to measure the sound velocity of iron at more higher pressure, for example, 400 gigapascal over. thousandths. So at present, it can be said that the experimental limit for high sound velocity measurement for iron has been reached to around 300 gigapascal. So further, further measurement will require some kind of technical breakthrough, we think. This is the result of the relation between the sound velocity and the density of HCP iron. The result is from the density is 11.95 gram per cubic centimeter. The pressure is corresponded to 154 gigapascals, and to the density of 13.87 gram per cubic centimeter. Pressure is corresponded to 310 gigapascals. So these experimental conditions covered the density of, we plotted the seismic model of the VP of plane is as marked as this magenta color. So our measurement covered the density of plane in the core conditions. So as shown in this figure, even at this extreme pressure condition, the density to velocity relations of HCP ion can be expressed by following linear equations. But this linear relation is commonly referred to as Birch's law. So this is the result of combining our new Birch's law for HCP iron with the previous high temperature HCP iron experimental result. So for both VP and VS, the result are in reasonable agreement with the theoretical calculation, although there are some differences. So one of the major topics in the high-pressure earth science is that the density and sound velocity of pure iron under core conditions cannot account for the problem. So this is so-called the density or velocity density issue, density deficit issue. So here we show the newly estimated velocity deficit from our work. So the VP deficit is 2 to 4%, and the VS deficit is 29 to 36% from the comparison between HPI and the seismic model. So based on these results, we discussed the light element contained in the Earth's core. So there are many candidates for light element in the core, but geochemistry, meteorites, and/or numerical calculation suggests that silicon and sulfur may be major candidates. This figure shows the relation of sound velocity assumed under the inner core conditions for iron and iron compound with the plane. So this triangle composed of these three end members contains both of the VP and VS of plane. The compound of these three end members can account for the density and sound velocity of the plane. So thus the simplest constraint of light element that account for the plane is 3.8% silicon and 3.8% sulfur and 5.8% of nickel. So next, I present the result of our recent sound velocity measurement for iron light elements compound. This result is in review. So recently, we have studied our phase relation of iron nickel silicon alloy under high pressure and high temperature conditions, and we found that B2 structure, which is the ordered body-centered structure, and HCP structure coexist as a two-phase mixture in the high temperature result near the melting point. So, however, for more detailed implication of the core sound velocity measurement of iron nickel silicon alloy under high pressure and high temperature conditions are necessary. So, we performed the high temperature sound velocity measurement of these materials. So, we use the sample of B surface of iron nickel silicon alloys. So here I present the result. So we measured the sound velocity of iron nickel silicon alloys at the high temperature condition up to 130 gigapascals and 2300 kelvins. So this figure shows a typical example of IX profile of with iron nickel silicon alloy at 130 gigapascals and 1700 kelvins. So here I present the result of relation between the density and sound velocity of these iron nickel silicon alloys. These open circles represent the previous result at ambient conditions. This solid colored square represents our recent result. So as you can see, so sorry, as you can see, the sound density and to sound velocity relation under high temperature conditions is almost overlapped the result of ambient temperature conditions. So at least this structure of iron nickel silicon alloy has very weak temperature dependence or negligible temperature dependence. So there are other iron compounds that have such weak temperature dependence for the such as the iron silicon alloys with B20 structure or some other things. So the presence of or absence of temperature dependence and its tendency is so important in comparing the sound velocity of iron alloys with flame. So to constrain the light element in the core, we are working on it to investigate the iron light element such as sulfur, carbon, oxygen, or hydrogen, etc. And finally, I want to present sound velocity measurement of rhenium at multi-megabar pressures and primary pressure scale derived from these measurements. So the pressure scale used to evaluate the high pressure experiment is an important factor in high pressure experiment. So the et al. 2000 proposed the method of thermodynamically determine a primary pressure scale from the definition of the pressure derived with respect to density by simultaneously measuring the density and the sound velocity or elastic constant. Now, in most previous work on the primary pressure scale using this other method, the density was measured by XRD and the sound velocity or elastic constant were measured by ultrasonic measurement or brilliant scattering measurement. So in this study, in order to perform measurement at experimental pressure, we attempt to the measurement of sound velocity by the IXS measurement using polycrystalline samples. So we choose the rhenium metal as a sample because rhenium is a heavier element that is expected to produce strong excess contribution and is also often used as a gasket material in high pressure experiments. So this figure shows an example of the IXS spectra of rhenium under the ambient condition. These blue peaks are the LA mode and these red peaks are TA mode of rhenium metal. So both when we plot as a dispersion curve, we got the VP and VS. So the sound velocity obtained by the IX measurement, both VP and VS of rhenium are consistent with the previous ultrasonic measurement. So our VP and VS by using IXS and compared with the VP and VS by ultrasonic measurement. These values are consistent within the errors. So here are the results at the under the high pressure conditions. So this figure shows a typical example of IX spectra of rhenium at multi-megawatt pressures over 200 gigapascal. So even at such higher pressure, both LA contribution and TA contribution from rhenium have been clearly observed. So these are the dispersion curves for all our high pressure experiment. And this figure shows the result of relation between density and sound velocity of rhenium. So compared to previous result, our VP is consistent with the theoretical calculation of Stein-Newman 1999, but slower than the theoretical calculation of Louvre 2012 and the excellent result of Duffy 1999. On the other hand, the VS shows the opposite result. So our VS is consistent with Louvre and Duffy, but much faster than the Stein-Newman. In particular, for the VP, the difference between our result and Louvre's theoretical calculation becomes much larger with increasing pressures. So this black solid curve shows our newly determined primary pressure scale of rhenium. So compared with the previous rhenium scale, our scale is consistent below 60 gigapascal, but the difference gradually increases from 85 gigapascal, and the difference becomes large, exceeding the error above 120 gigapascals. So using our new rhenium scale, we perform high pressure compression experiment of pure iron. So this result shows the pure iron under the Earth's inner core condition may be heavier or denser than previous thought. So this suggests that the Earth's inner core may contain more light element than previous thought. To account for the density deficit compared with the premise-seismic model. So further work is in progress to investigate this result. For example, we are attempting to determine and comparing multi-megawatt primary pressure scale using our methods through IXS sound velocity measurement. So here is the summary of today's my talk. Thank you for your attention, and I would like to also to thank all the institution and grant for our works. Thank you very much.
Thank you. Thank you for a very nice talk. Are there any questions for the speaker? couple of quick ones.
Yes.
You mentioned that you're doing your measurements at 100 to 150 gigapascals. Can you translate that into the depth of the Earth's crust?
そう、そうや、アースズクラスって。
No, so at what depth in the Earth's interior is 100 to 150 gigapascals? Pascals.
sorry. I will go to the first page.
I forgot what slide it's on.
100 to 150 is around the boundary of lower mantle and outer
Oh, okay,
cores.
right at the
So the boundary of lower mantle and outer core is about 135 gigapascals.
Oh, okay, right, yeah, that's a nice figure. I have to look at that figure. The depth profile. Uh, oh, right. Okay, thank you. Thank you for making it bigger. I see. Um, and now, so in terms of the phonons, I mean, these are these regular phonons, or do new type of phenomena occur at that pressure?
I The IX observation itself is regular, but as I talked, the IXS contribution is very weak compared with the inelastic contribution is very weak compared with the general elastic contribution. So we developed our newly designed measurement system to get or to identify the very weak IXS contribution. Normally, previous, previously, it, 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 it is hidden by the background or
Okay,
noise. So when we improved our measurement system, まあ、this led is previously
right.
the measurement of previous system. So there it seems something around here what we cannot identify, but when we use our newly designed system, then we can get such small, such big peaks.
Thank you. Are there any other questions for the speaker? Can I ask one last question about the Spring 8.2 upgrade? Spring,
Spring 8 upgrade?
Spring 8.2 upgrade. Yeah.
Spring
So
8 too?
yeah. So uh, are you increasing the number of beamlines, increasing the current in the storage ring, increasing the intensity? So what are the key features of the upgrade?
The, of course, I am not the beamline scientist of Spring
Okay.
8, but the most strong point is the brightness of the beam. So they expected to the brightness become above 100 times brightness
Gotcha. Okay.
compared with the current Spring 8.
Right.
So if the upgrade succeeded,
Okay.
we not only us, so many scientists can see the, for example, very small sample
Right.
or
Okay.
we can expect more good signal to noise ratio. Or
Yeah. Okay. Well, thank you for a very nice talk. Let's give the speaker a round of applause.
okay,
And
thank you very much. So I will
I'd like to give a thumbs
I
up.
stop the
Well, thank you. So now let us move to the next speaker who is here, and I believe that is Mac Magundura? Is that you? I probably did not pronounce that correctly. I'm sorry.
I'm supposed to talk at 10, in 30 minutes.
In 30 minutes.
Yes.
Oh, I'm sorry. I did this out of order. Sorry.
Hmm.
Let's see. Let me make sure. The next speaker is Marcel, who I do not see. So I
I
don't.
don't think it's I don't think it's online. Maybe we try to swap.
We could do that, or we can just. Do you want to, or Mac? Do you want to wait until your time, or do you want to start now?
Better to wait because if one or two students have to join, they have the schedule.
Gotcha. Okay. All right. We
Okay.
will wait for your time and just go on a. Well, we'll wait and see if. Well, I guess if Marcel was come, they'd already be 8 minutes late.
Mhm.
Uh, okay. So we'll wait. We'll start your talk on time at in 12 minutes.
Good. I'm there. Yeah.
Good morning.
Hello, good morning.
I'm Serin Biragay from Dakar.
Okay, hi.
Morning.
Hi.
We'll start in 5 minutes. Okay, let's get started with our next speaker.
Yeah.
And that is Mac.
Mac ممكن مقدرها Chewbacca.
Okay, thank you. I'm
Yeah.
sorry if I I was definitely going to mispronounce that.
Yeah.
You can go ahead and share your screen and start your talk.
Let me try. Can you see the screen?
Yes, it's come up and it's in presentation mode as far as I can see. Thank you.
Okay, good. So maybe I need to close the camera so I can decrease the solicitation of the network. So,
Okay, that's fine.
uh, So, as I said, I'm Mac Mugumadera Chubaka from DRC in Bukavu. Our institution is called Institut Supérieur Pédagogique de Bukavu. And I'm from Department of Physics there, but also I collaborate with Tracer Lab, a startup in Belgium focusing on traceability, the support to artisanal scanning, artisanal mining also. The outline of my talk will have 4 points. The introduction, materials, results, and discussion, and I will close with conclusion in this presentation. As you know, coltan is a concatenation of columbite and tantalite. As you can see, let me see if I can throw I lost the laser. So I see. Here it is, I think. Okay, this is good. The structure is like this figure. You can see it's a combination of iron, tantalum, niobium, oxygen in this kind of structure. And red balls correspond to oxygen, orange balls correspond to iron, and the manganese. When it comes to coltan, yellow balls are tantalum and niobium. This structure is called orthorhombic structure in physics. We have two for in coordination we have 2 for the iron atom and 5 for tantalum and niobium. The structure, the material is known to be paramagnetics, and the density is between 5.2 to 8.2. When it's come to properties of an niobium or a tantalum, I showed the tab here, which show that the abundance of for tantalum, for example, is 0.5, niobium is 8. It can be considered as rare metals. As aspects are shown there, this interesting properties of those metals attract they are applied in new technology due to their properties. As you all know, when it comes to tantalum, it's basically used as for energy storage in electronics, and the demand is increasing as the technology is growing in our days. Tantalum also, the facility we have with tantalum is we can fabricate this capacitor using, as tantalum is metallic conductor, so the oxidation of tantalum can already constitute the dielectric interfaces, so you reduce the size of the component, and it's why it's preferred to other component in electronics when it comes to reduce the size of the component. There is other application due to thermal resistance, corrosion prevention, but also we can use tantalum with carbon for coating for strength layers. When it comes to niobium, niobium is also used in orthopedic implant, but also in superalloys for aerospace equipment, superconducting coil, and so on. I like the two examples. For example, for superalloys, there is a bridge between in France what we call Milo Valley Bridge. By using only 0.025% of niobium in the steel, they reduced by 60% the weight of the bridge. You can imagine the saved money and the way they reach this project. There is another one between Sweden and Denmark. By adding only 0.022 percentage of niobium in steel, they reduced by 15 kilotons of the weight of the bridge, and so saved about 25 million of dollar by constructing this bridge. It means this show how interesting is niobium in superalloys. But the main problem with those material is mainly associated with conflicts, and so a concept of conflict minerals arises since I think 2005, around 2000, and when it comes to conflict mineral, it includes all three Tg metals. The three T refer to tin, tantalum, tungsten, and gold. Mainly, as you know, in DRC, mainly in my town, we are again experiencing this question of war, where rebels are controlling two towns in the east of Congo. And this raises again the question, can we overcome this situation? How we deal with this situation? And so there is a need to work to try to see if we can make this business reliable, and so we try to do our best locally. Things are difficult locally because most of those minerals come from artisanal mining. When you can check AfPS, AfPS is a Belgian institute which is interested in the east of Congo and try to map all artisanal mining sites in DRC. About 3,000 of sites was identified until 2020, and most of them are located in the east of the DRC. You can see, of course, gold represents the most important part of the cake, but for coltan and which was our main interest at this period, it's about 7% of the identified sites. The way people are working on sites is a poor situation. The miner, you can see different picture there. Miner at a new investigating, try to find the minerals. They are washing their production in the rivers. Sometimes they are not well equipped when they go in the pits. Mainly the pit is accidental, so no protection, no safety, and so on. And those aspects affect the way this mineral are mined locally. So if we need to be compliant and to align with requirement of the market, this situation need to be changed and need to be investigated. So we started since I think 2018 working installing a facility for chemical physics treatment and application, mainly focusing on coltan. We had in this project 4 work packages. One related to sustainable technique for purification and separation of tantalum and niobium locally, to highlight the new challenge to extend tantalum and niobium valorization while strengthening local expertise. But also we have also we're focusing on mineral from certified sites, which needs to be characterized to improve the information to operator, artisanal miners for an added value, so they can also take different precaution for safety and for traceability. We have also to draft some recommendation for the better investigation and improvement of artisanal mining sector, in order to expect that different stakeholders take advantage or exploit those recommendations to improve the situation locally. This presentation is mainly related to the said work packages, which are focusing on mineral characterization in order to expect someone can improve the know-how of artisanal miner, but also if we can pave the way for the traceability. So to do so, to achieve this, we want to on different sites. Here we have different region: Numbi, Kankanda, Wimbi, and we collected a quantity of samples. The one in this paper, we collect about, we analyzed, I think 15 samples from different sites. The sites are indicated on different map. We geolocalize the site, the sample, and we collect about 10 kilograms per sites. So we can, after that, we can grind them to homogenize to obtain a composite which will be analyzed. To make sure our researchers are safe on sites, they go with portable Geiger Miller equipment to check at each time the radioactivity of the sample. We have the same equipment in the lab also. When we have the sample in the lab, they are gridded and to reduce the size at less than 45 micrometer. And then they are, before that, we dry them at 90 degree centigrade. Homogenized samples then are analyzed by a portable XRF equipment. This one, the principle is known. The X-ray X-ray photon are sent to the sample and excite some, eject some electron, and the upper electron on upper level can come and fill the hole and emit another X-ray, which is characteristic of each material, so we can discriminate different elements which constitutes the sample. This one is where this one was compared the measurement. We locally we do XRF, but we are able also to do a complementary analysis by photon-induced X-ray emission, by X-ray photo emission, and ICP AES also, using our collaboration in Belgium. For mineralogical inspection, basically we used 2D fractometer for Numbi and Lulingu. Sample was performed using Bruker date echo diffractometer. For Kankanda and Wimby, we use Pananalytical Expert Pro because it depends on when you conduct the measurement. One equipment, the Pananalytical equipment is from University of Liège, but Bruker is from the University of Namur. Both equipment use a copper source, and the sample was scanned between 3 degree and 72 theta at the rate of 0.02 theta per second. Then, when I will recommend you to see, I will not show all the diagram related to the diffraction measurement, but I recommend you to read the whole paper so you can see the all information. But the identification of all phases for the axis RD pattern was carried out using Pananalytical expert suite and web PDF 4 plus IC DD relation database, and completed with match software. Coming to the results, mainly what we found with this equipment is that our samples and or composites are mainly constituted by tin, iron, manganese, silicon, and the target element, which are tantalum, niobium, of course. And we compared our measurement to that from photon-induced X-ray emission and ICP AES, and we have a good correlation. As we can see, this is, for example, a sample from Numbi. XRF measurement are compared to proton-induced X-ray emission, and you can see there is a good correlation between measure from for both techniques. We checked also. We can see this is peaks, and in horizontal we have XRF measurement. And also we compared that from NUMBI using ICP measurement. Also, we have a good correlation. Mainly, we take into account the main component of the sample. Is why we consider manganese, titanium, niobium, aluminum, iron, tantalum, silicon, and tin oxides. From Lulingu, the same situation. Okay, good correlation also. We have 0.99 of correspondence. This fit better with other measurement. This one is from Lulingu again, when we compare XRF and ICP. Here we have samples from Kankanda, and we achieved this. We are able to show that measurement conducted with XRF and PIX and ICP, all three can fit together and give good information about the samples. When it comes to we can compare also. Okay, this one is hiding some part of it. When we compare, for example, niobium and tantalum, this is the main element we target in the sample. We compare tin to tantalum. We compare tin to tantalum and niobium proportion. There is also, we can discriminate different samples from each origin. So we have different information, useful information based on the composition. We can see in the figure also, we can really discriminate the sample coming from sorry, we can discriminate sample coming from Lulingu, sample coming from Numbi, sample coming from Wimbi, sample coming from Kankanda, and all four captures show clearly that there is difference between the different sample based on their origin, and this discrimination was done using the major or the main element, I mean niobium, tantalum, and the tin. We went also to check ternary diagram. All those data was from XRF. In the figure, you can see we refer to sample from this one is the figure refer the point which refer, for example, for sample from Lulingu. Different color, you can see the point, the details is there. One point, you have the diagram. One corner you have tin, another corner you have tantalum and niobium, and there is other element constituting the sample. As you can see, the point referred to sample from Lulingu, Mwenga, and Kanganda area are aligned there, aligned on the line that points to the tantalum plus niobium pole. This indicates that the sample are mainly composed of columbite, tantalite minerals. Conversely, point associated with NUMBI samples move away from tantalum pole line to tin pole. This define cassiterite dominance in the NUMBI sample, and in the second diagram, they show clearly the predominance of tantalum, niobium, and oxides, considering the proportion of represented by the three metals. The dispersion here is not the same or as on the left diagram. This we went also on checking the trace element accompanying which come with the major element, and we draw. This is what we call a spider diagram. The spider diagram usually is used in geology to investigate elemental composition compared to a source of such a bulk if material. And here, the concentration of traces, the one we identified, we have there different material. The main element are tantalum here, and niobium, but also we have some impurities which come with the major elements, so we can see how it progress, how it influence, how it change from sample to sample. The first diagram is from Numbi, the second one is from Lulingu, the third one is from Kankanga, the fourth one is from Wimbi. And all this come from XRF measurements, which compared to other technique, which is more sensible than other techniques. So we can see the real difference between discriminating the four samples from different sites or from different areas. We checked also the radioactivity of the samples, and we have good information. As we are focusing also, we aim at safety of artisanal and minor, but also all stakeholders involved in the value chain of these materials. You can see different sites, but also we have different composites of the samples. As you can see from well-known recommendation, you have the efficacy dose must be below 3 millisievert per EA. But when we compare, for example, the dashed line in blue here refer to the say required for pregnant women, for example, you can see only pregnant women can be affected by such a radioactivity if they remain in the site. But we are aware that men, children, pregnant women, young people also work on different sites. So giving this information is a way to make them working safely in in that zone, and also to make sure we communicate properly to have a feedback to those persons from whom we collect the sample. The calculated radioactivity showed that the more radioactive site was Musokole. If you compare the radioactivity on the diagram, but some of them can be very, very low, like Mungwe 2, Koet. This is close to Numbi. We are very glad to contribute by this study because from our conclusion, we showed that portable XRF spectrometer is a tool to fingerprint columbite tantalite ores. And as shown, we have a good agreement, we have good correlation with data obtained from proton-induced X-ray emission, but also by ICP AES mineralogical analyze, and the result showed that columbite tantalite appear in the form of columbite phase, which is a combination of niobium, tantalum, iron, and manganese. From discrimination diagram, we are able to show that columbite tantalite or can be discriminated from one to another one according to their origin. Sample contain tantalum and niobium as well as important metal such as titanium and tin, but as on the market, mainly, for example, in DRC in Congo, coltan is traded only by taking into account the concentration of the tantalum, showing the real proportion of valuable metal which come with tantalum can be a key parameter to renegotiate maybe the price of the material locally and to improve the revenue of the all artisanal miner which suffer from which don't gain a lot in their work. Chemical analysis also revealed the presence of radioactive metals, mainly which call for recommendation for artisanal miner when exposed to the materials. They are there 1 month, 2 months, working with without security, without any equipment. So we have to communicate on this issue, on this matter, so they can behave differently and work safely. The dose appear to be low, as you saw, in some cases. It appear done, but when it comes to pregnant women, it can be risky to work there. So they can be affected, and their presence in the mine should be discouraged. An environmental issue also. You saw that from non-practices, they usually wash the sample in the river. It means this material can be spread in the water. So we have to inform on the radiation dose from the radioactive dust inhaled during the columbite tantalite extraction and processing. The initial radioactivity is almost entirely contained in the ore residue and is therefore seriously contaminating the region of water. So we have to alert, and government or regulation must be drafted about the practice on the artisanal mining. Hopefully, our conclusion will provide decision maker, artisanal miner, researcher, and investor with elements that will enhance their knowledge of Colombo tantalite or columbite tantalite or fingerprint in DRC. And so we expect this study to contribute for better world, for better business, for better well-being on the artisanal mining. Thank you very much. I would like to thank all the collaborators for this study, mainly Shikika, who conducted his PhD on this on the matter, working on the purification. We have many publications which can be read on how we were able to extract, to separate tantalum from niobium while understanding the different composition of the sample from different locations. We have money for that from ARES. ARES is Académie de la Recherche d'Enseignement Supérieur in Belgium. Other data were from different student master thesis, Nathan, Sophie. We are able, through collaboration with University of Liège and Namur, perform some experiment which were not able to do locally. So we'd like to thank all the contributors from contribution with money, contribution with knowledge, contribution with collecting samples. Thank you for your attention.
Thank you for a wonderful talk. Are there any questions for the speaker? Yes, I see. Is that? I can't pronounce your name. Diagradas?
Thank you. I know you struggle to pronounce the name. It's not your problem. It should be mine. Okay. Thanks to the speaker. Thank you for the presentation. It's interesting. From that part from Bukavu where there's been a lot going on lately and for many years. And now mine is about your direct link with government, because this information from your results, your findings, especially in terms of radiation doses, and I imagine that the regulation there, if there is a government at all, I don't know how far you as researchers are connected to the government so that your findings directly influence policy. Because when we get these in presentations and you say it could inform government, is there direct link? Because like now, in those mines, you find pregnant women, as you say, the women who are doing this thing. So is there a direct link between your research and government so that there's a direct policy information basing on your findings? Thank you.
When we start the project, now we are experiencing rebels control in our region, but this project starts in 2019. And we had a close link with administration, even from the formulation of the project. And also we had to organize annual meeting to show how the project is going. And before the war, before Bukavu to be controlled, I was also in Kinshasa discussing, presenting all these results. And for me, my expectation was to develop now a pilot locally, but things changed a lot. So I think we will keep this data until we expect again to discuss with the government to see how we can progress with this research and how we can take advantage of all produced knowledge, but they were involved, of course, in the discussion. We present also our findings in August 2024, but in 2025 it was not possible to discuss with them due to the situation we have now in our region.
Thank you. I have a couple of questions. First is you mentioned that the material is paramagnetic. Have you done a quantum calculation or any type of experiment that will inform you where the lone spin is located?
This not yet, but for this first step, we conduct only, we are working basically, when we do from separation already, people are able to discriminate, for example, the magnetic materials with the targeted materials.
Mhm.
This is one aspect of the practice, the local practice on site. But no real experiment, no real measurement was done to determine the real property of the magnetic paramagnetic properties. This is from literature, and we correlate with the practice also conducted on ground, on field.
And my second question is, I just came across the, I guess it was a few years ago, the launch of a Center of Excellence in Advanced Battery Research in the DRC. I just put a link in the chat actually on about that. And I was wondering if you or any of your colleagues have been involved with that Center of Excellence on battery research, because it would seem like it would depend a lot on the finding of new mineral materials.
That's good too. Maybe I will contact, I'll see what they are doing. It's better. Mainly now we are wondering if we will continue to work on this matter question locally, or we have to switch to try to see what is happening, for example, in Katanga. I think this is a good idea, so I will try to see what they are doing and try to contact them and see if there is a frame of collaboration, and try to see what we can do with them.
That'd be great, because I tried to contact the university, but my French was not good enough to converse at that level. So
yeah, but I know some guys in Lubumbashi. Maybe I can contact them and try to see. I used to, when I heard first time about this center, I understood that there is one in a previous researcher in Bukavu who was involved. I think it can be a good channel to reach them and try to see if we can have a discussion and try to understand what they are doing and how we can construct on common project.
okay, that's good. Let's work together on that. I'll be in touch with you. Are there any other questions for the speaker? Then with that, let us close the session, take a quick break, and we'll try to start in 3 to 5 minutes.
Thank you.
Thanks.
Hello, Lawrence.
Yes.
How are you?
Okay.
When Bira is going to talk?
So what we have coming up is a session that is
because I see that he is online.
full. Yeah. So what we have now for this next session is it's full, but not everyone shows up. So what we can do is see if there is going to be any situation where a hole is put into the schedule.
Because I want to listen to his talk.
I understand. So
because
I don't see
at the same time following also at ASAP. So I want to know at what time, so that I will know when to.
I don't see the first speaker. So that might be the opportunity. The first speaker is Jabel Mahamoud. Who we think? I don't see that speaker, so he may be able to take the first slot here. Your friend Professor Gay.
Okay, and now the break is for.
The break was the last talk went a little long, but the session should start really in 1 minute. But we'll start in like.
Okay, in 1 minute. So okay.
So if Professor Gay is available, he may be able to take this time slot.
Yes, he's online. I hope that is.
Okay. I don't see the first speaker.
Okay, okay.
And I don't see any. There were some speakers yesterday that missed their time slot, and we tried to make a space for them, but I don't see any of them either.
Make a point here. What you are saying, Simon, is correct. But it's still that these are institutions by themselves.
Allô,
Yeah.
Bira, tu as entendu ce qu'il a dit? Bira, tu es en ligne? Allô?
So, Professor Gay, are you ready to give a talk right now?
So you're comparing different things.
Vera, are you ready to give a talk right now?
You can go to the new CLS.
He's online, but I didn't.
He might be still away. Can you send? I guess you're in touch with him by WhatsApp. You can send him a message and say that he can give his talk right now, because I don't see the speaker that is supposed to speak right now.
Okay, okay. Let me try to contact you.
This is not a lab. It is a machine integrated in a lab or in a camera. You have dedicated structures. And then you think what time shorter than here, because these infrastructure, you have to use Photoshop, whatever. To build this solution, you just need, as I said, a university willing to be funded and build the machine.
So Lawrence, none of the speaker is available?
I don't see the first one, and I don't see the second
Let's
one
try to
either.
swap then. Let's put them on the app, on the WhatsApp. So that might work.
Professor Wege is trying to find a colleague of his who had wanted to find a slot, but I couldn't guarantee him a slot. I told him he would just have to show up to the session. And
okay, donc il t'attend, hein?
I mean, it has to be now because we want to stay
Yes,
on
he's coming. He's coming.
All right, Prof. Okay, that's fine.
He's coming. I told him. He said he's coming.
And if you know the Prof. Wage, if you know the rest of the speaker, you can as well try to talk to them on WhatsApp.
Yeah.
When what?
Hello. Hello.
Oui.
Yes, you can start your talk right now.
Okay. I share my screen. Hello.
Oui. Allez maintenant, please.
Hello.
Oui.
Oui, on t'entend.
Hein? Okay. Thank you very much. Hello, dear participants. My name is Serigne Biragay. I'm professor of electronics, specializing in high frequency and microwave in the Department of Physics at the Faculty of Science and Technology of the University Cheikh Anta Diop of Dakar. I will present you previous work on RFQ, radio frequency quadrupole. Donc, I aim with this work to present opportunities for young African researchers to explore the machine that make accelerate particle beams. What are radio frequency for dipole? That's a device used for Linux as injector. As we see, 4-pole, it can focus in one direction, X direction, and defocus in Y direction. And alternately. That's a structure that make or that present a photo structure, photo focusing, defocusing, and in average it focus. So, we have a structure alternating gradient focusing, and it was invented by two Russian, Kapczynski and Tepliakov. And as we know, an RFQ that is not modulated cannot have an axial electrical field. In order to get it, we have to modulate the vane, so it appears an axial electrical field. In the beam region, the field can approximate it as to be linear. So as I show. Then with this device has three properties. It can focus particle beam and bench it, and so also accelerate this beam. We have done a concurrence with the focusing and the accelerating properties. Now I show the factor of focusing and also the factor for the acceleration. Now, the particle beam in transverse direction can be explored, and it obeys the Mathieu equation, as you see. The stability criterion can be also explored, and this Mathieu equation can be resolved. So, the longitudinal beam dynamics can be studied also with this diagram that gives the stability region, and we can make a particle in cell simulation with the normalized velocity as it is given, the kinetic energy that we expected, the power, input power, and the beam current. So this structure can have confluence. So the bandwidth which can be very large in the gigahertz region. So here is some RF parameters for beam simulation. So, and I show you a structure that has been constructed and measured. So we have a periodic structure in X direction, and so in Y direction, the vane. Here is the, we have a discreted vane in its work. So the scattering parameters have been measured and compared with the simulation. And so the transmission parameters, scattering parameters also, reflection and transmission. and we have done a bit pole measurement. Donc, this is a perturbation measurement. That's show the field that is in the structure. So in polar diagram that show the quadrupole here, the quadrupole mode can be shown. So, and we make the particle cell computation and prove that the RF quadrupole in gigahertz region has the properties that we expected. We see the continuous beam injected and a phase that shape the bunch, and at the end of section we see the bunch that can be have been accelerated. So that is the work that I have. I aim to share with you, and so also I have to see some possible work that can be interest the African young researcher. So we can use the tools that is developed by German Gedefidel, and we can obtain license in Senegal for our students or our colleague in order to explore devices with this tool. The Gedefidel, this is developed by Werner Bruns at the TU Berlin, Technische Universität Berlin. And also, I will show and stop my presentation. Gedefidel, developed by Werner Bruns, and what I have, what I want to show is that we can in Africa work in this domain and have interesting result, and we can place we can make a challenge in this field, even if we are in Africa. Sorry, my English is not so fluent, but I have I want to share with you this possible work in LINAC, linear accelerator, and we have we are open to collaborate with with other African in this domain. Thank you very much.
Thank you. Are there any questions for this speaker? No speakers, no questions, then we'll thank the speaker. Oh, go ahead with your question, please, Mac.
Yes, it's Mac now. I was checking on the schedule. I didn't find the abstract related to the presentation. I understood that he took only the slot to present the project. Maybe if you can have some links, a web page where we can get more information, it can be good.
Yes, good suggestion. So, Professor Gay, could you send to the conference some kind of abstract or your slides? Your slides might be good enough.
Yeah.
And send that right away.
Okay.
All right. Thank you.
Thank
I
you
have
very
a
much.
question.
Professor
Lawrence,
Wege, go ahead.
I just want to ask him, what is the INAC? Because this is an acronym or what?
Okay, linear accelerator.
What is INAC?
LINAC.
Yes.
Linear accelerator. Linear accelerator. Donc, as you see in African light source, we have to inject the beam, the particle beam. Donc, the physicians, the physicists work on the particle, on the beam, but the beam has to be injected with the machine. And the machine, one of this machine is the linear accelerator. And the first part of linear accelerator, after the klystron, you have an RFQ, radio frequency quadrupole, as injector.
No, my question is, what is LINAC? What is mean? It is linear accelerator or something like that?
Linear accelerator.
Huh?
Linear accelerator. Donc, the linear accelerator is the injector. We inject the beam in the ring.
And forget that name.
Okay, thank you.
And a little characterize.
Thank you.
Thank you, Alex. Now, I will send you some paper on this topic. Thank you very much.
Okay, thank you. So we'll move on to the next speaker, who I don't know is here. I don't see the next speaker. Is that would be Derajay Dadi? I don't see Deraj. Is Dipti Sahu here? And Awad Muhammad. I don't see.
Yes, I'm here.
Oh, you are
Awad
here.
Muhammad.
Okay, so now your talk was supposed to begin at 11:30. So
Yes.
half
Exactly.
So you can either go now,
For me, it's
or
fine. Yes.
you can wait until your time. What's your preference?
I can start even now, no problem. If the other speaker not ready yet, so
Yep. Okay. So if Professor Gay can stop sharing his screen. And then Awad can start.
he can stop sharing. So,
Did he? Let me just stop. Let me do this. Hold on one second. So that stops sharing him. So now what I can do is the following. What I stop sharing. And you can start sharing now.
okay.
That was weird. Let's see. So, okay, we're good.
Good morning, everybody. Good afternoon for all participants. My name is Awad Al-Amin Awad. I'm PhD student, University of Cameroon at Physics Department. I'm doing recently my PhD University of Cameroon in collaboration with CNR Laboratory at Elettra-Synchrotron Trieste in Italy. So mainly my research focus on the photoionization of low and highly charged atomic ions using synchrotron and free electron laser. First, I would like to thank the organizer of the African Light Source and also the African Physical Society of giving this opportunity for giving my talk today. So my outline, I will share the my research in gas phase beamline and most beamline at Elytra. Then I will speak about the instrumentation has been used for this research, mainly EBIT and octo-ion guide. Then I will present some results from both instrumentation. And also at the very end, I will present some data from European exfil data at Hamburg, Germany. So the gas phase beamline, as you have been here in the previous session, in the last days, about the synchrotron and the beamline characteristic. So mainly the gas phase at Elytra, it has insertion device of undulator of length of periodicity 12.5 millimeter. The main component of the beamline is the monochromator, which is a variable angle spherical grating monochromator. The experimental end station normally 1.7 meter from the ground. So all these components represent the optical properties of the beamline to guide the photon beam until the end station. So here we have also entrance and exit slits, which also contribute and controlling the resolution of the beamline. The other beamline is called MOST at Chibo. It has the energy range of the gas phase beamline between 13 to 900 electron volt, while the flux from 10 to the power 11, 10 to the power 12, with resolution of 10,000. The second beamline we have used in this measurement is most achievable beamline. It has two undulator insertion device, Q, which refers to high energy undulator, LEO, which refers to low energy undulator. So the main difference between the gas phase and MOST, we have in the low energy range, we can use NIM, normal incident monochromator, which is used to source like gold or aluminum, or spherical grating monochromator, which is the same as the gas phase. The energy range in Chibo from 10 to 1000 electron volt with 10 to the power 9 to 10 to the power 11 flux, with lower resolving power of 5,000. I would like to indicate these two beamlines. They will be, as you know now, Elytra under upgrade to Elytra 2.0. So both these beamlines, they will be combined in one beamline. So like main beamline and also a branch beamline. In the future, if someone needs to apply for a proposal, he has to refer the most beamline, which is mainly will be called. I will speak about the first instrumentation has been used and conducted the data in this research, electron beam ion trap. So the main idea of the electron beam ion trap has been developed firstly in Max Planck Institute in Germany. So this sort of collaboration between the Max Planck Institute and CNR in Elytra, we just bring the end station from Germany to Italy and perform our experiment. The main component of the electron beam ion trap is electron gum, which provide electron beam for in the soft X-ray, which produce highly charged ions. The main purpose of this instrumentation to produce highly charged ions and also to confine them to allow to interact with the synchrotron radiation. As you can see here, we have a set of drift detector from DT1 to DT6. DT1, DT2 responsible of guiding the electron beam towards the interaction region, where it takes place at DT4, where we can inject the neutral gas. DT3, DT5 responsible of confining the highly charged ions axially. And also you can see here, we have set of magnet. This has been set in the central bar to confine also the highly charged ion radial. So we have two different confinement of the highly charged ion. The detection of this ion, we can use the detector as represented in the top, and also like vertical and horizontal to the highly charged ion produced. Also, we can detect the ion, the auto-ionized ion using mass spectrometer after DT6. So at the end of the interaction with the synchrotron with the highly charged ions, we are able to select the highly charged ions in the using mass spectrometer. Here we have real picture of the setup. Here in this image, we can see in the blue rectangular is the electron beam ion trap. In the back of the electron beam ion trap, we use a spectrometer that has been used for energy calibration. And actually, it plays a very important role in our case, especially for the energy calibration, because we are dealing with high resolution of the highly charged ions, and we are interested in very resonance of these ions, so normally of sub of milli-electron volt. Here I will give, because of the importance of the spectrometer, I will speak a bit about the spectrometer. It has entrance slits, which allows the electron beam to enter. Then we have two grating 1 and grating 2. And then we have the CCD detector. So the grating 1 for lower energy in the XUV range and grating 2 for high energy range. So the idea to have the source from the synchrotron, and then it hit the grating of the spectrometer, and then you reflect this light and you detect it in the back of the SDD CCD detector. Here I'm showing like example of some result from the spectrometer before installation of the EBIT. We have tested this spectrometer with absorption of argon from energy range from 244 to 256 electron volt. And we are able to even resolve one single of this peak very highly using this spectrometer. This proof we can use the spectrometer for this highly resolution measurement. For sure, as using a spectrometer, we need to calibrate our data. So for calibration, we use a different set of lines, very well known theoretically. So in the gas cell of the beamline, we can measure the helium-like nitrogen at different charge states, K beta and K alpha, and also NW in the main of the electron beam ion, in the center of the electron beam ion trap. And also we measured N5 plus K beta and also N5 plus K gamma. So this peak represented in the pixel. So we need to convert all this energy pixel to photon energy. So what we do, we know this line theoretically in electron volt. We fit this peak using Gaussian peak, and then the center of this peak, we plot it again as theoretical electron energy, and we extract the relation between the pixel and photon energy. Then we are able to convert all the pixel to photon energy range. One of the interesting measurements has been done using the electron beam ion trap at highly charged ions is N3+. So the EBIT or the electron beam ion trap allow us to predict data from using the fluorescence yield in the central of the electron beam ion trap. We can detect this data using SDT detector, which is represented in the right bar in the figure. At the same time, and this is the process of the photoexcitation. So you have the N2 plus in the center of the EBIT, then synchrotron radiation came to N2 plus, and then you photoionize to N3 plus. So you have removal of another electron. After the de-excitation, you have the auto-ionization, and this can be detected using the mass spectrometer at the back of the EBIT. So here we represent the mass spectrum of different charge states. So in the EBIT, you can have different charge states from the background because it contains like water, and you have argon, and you have different species. So in this case, we can select the right ion by using a set of calibration. So we calibrate all these charge state with their mass to charge ratio. Here we show the zoomed stripe around 2.65. We have the resonance yield of N3 plus, and this plotted in the x-axis with the time of flight, and also in the y-axis with the photon energy. Here I'm showing also another case study from the electron beam ion trap. Here, the previous study was concerning highly charged ions of nitrogen. Here, we represent highly charged ions of oxygen. In this case study, we are interested to measure the energy shift between two isotopes of oxygen, oxygen 16 and oxygen 18. So the idea to have injection of oxygen into the central part of the EBIT, then you photoionize, and then you have the photoionization from oxygen 4 plus to oxygen 5 plus on the using synchrotron radiation. So the first part of the overview, here I'm showing the resonant and non-resonant photoionization of the species. So as you can see, you have different charge state, N4 plus, carbon C plus, and this mainly from the background in the EBIT. And also you have here oxygen 4 plus and oxygen 5 plus. So this has been produced by electron beam ion trap before the synchrotron. So we are making sure you have the right target ion species. After the photoionization, you photoionize from oxygen 4 plus to oxygen 5 plus, and then you can measure the photoionized species. Here in the plot C, we can sum all these spectra along the y-axis, and you can get the resonant peak of the red part representing the oxygen 5 plus from oxygen 16, and the blue plot representing the oxygen 5 plus from the oxygen 18. And we determine this shift is very small, around 2 milli-electron volt between the two resonance. This paper has been submitted recently to BRL with a collaborator from Germany. Another case of study, we revisited the famous Hanel effect. This mainly to study the effect of the atomic number versus the cross-section ratio. So you have this case study, we used the highly charged ions of nitrogen 5 plus, and here we represent in the left part the fluorescence yield of K beta in the red dot point, and K delta of N5 plus. So here, this data has been collected as I showed previously in the EBIT. We are able to measure the fluorescence yield vertically and also horizontally. So on the small peak, this is data collected from the parallel SDT detector, while the second peak represents the vertical SDT detector. So simply you have two detectors to detect your data. We can observe in the K beta, the parallel SDT detector, we have a smaller peak, while in the vertical perpendicular SDT detector, we have more yield of the K beta. While in the K delta, we have only in the two peaks are not more or less in the same intensity state. So this can tell us that the two SDT detector, the fluorescence yield and the cross-section between the ratio of the parallel and the perpendicular shows a different n number. It has changing. So around n equal to, this is the atomic number, is very close to 0. By increasing the atomic number from 2 to 3 up to 7, it is very close to 1. And this changing drastically by increasing the atomic number. Also, this Hanel effect can enable us to determine the lifetime of this species. So from 2 to 7, it shows the lifetime of these species. So the idea is we use like theoretical equation, and from the parameter set, we fit this experimental data with the theoretical equation, and we will be able to, and we are be able to like drastically correlate this data with each other. This paper has been published by our collaborator also from beam time has been measured in the electrosynchrotron trace time. The second part of my research is, as I indicated, we are interested in highly charged ions and low charged ions. So we decided for the EBIT there was some difficulty with the low charged ions because you have highly charged species from the background. So normally the low charged state, they are recombined or has been interpreted by or collapsed by another species of the highly charged ions. So we decided at Electra to develop a new instrumentation to devote for low charged state. So what is called octo-ion guide. So the main idea of this setup, you have the ion source, you generate the low charge state, then you have the mass spectrometer, you select the right ion, and then you deflect by 90 degrees to allow the photon energy to interact with the low charge state in the interaction region, where you have the octoball ion guide of 40 centimeters. After the interaction of the synchrotron with the ion electron beam, we deflect again by 90 degrees towards the detectors. In the detection system, we have another mass analyzer, which select also the right ion, and then we have as the end neutron. So we characterize this setup first, like offline with the synchrotron to see here representing the mass spectrum. So we are able to generate low charge ions of krypton from krypton +1, krypton +2 up to krypton +4. So this ion someone can study very easily using this setup. So you select one of these species and then you photonize. For example, you start from krypton +1, then you photonize to krypton +2, and vice versa. You can go from a species to another species. Here, for example, representing different selection, and we are able, as you can see, we scan the mass from our octo-ion guide. We can see the background is completely zero except the selected ion. So that means you are making sure you have selected one species, and this species can be studied with the synchrotron and also with the free electron laser. This paper has been submitted recently also from our study. We did one test with the octoball ion guide with the synchrotron. So the idea to have a gas cell before your setup for any recalibration, where you can put neutral and then you have some sort of absorption. In our case, we use neutral xenon in the gas cell, and we are able to measure 5 peak, and this peak can be used for converting or calibrating our data. Here we are showing the photoionized of the xenon +1. So in the setup, we start from xenon +1, we deflect by 90 degrees to the central part of the octoball, and then we photoionize to xenon +2. And we see some resonance of Rydberg series from xenon +1 to xenon +2. Here I'm showing some study also from the electron beam ion trap has been done at XFEL in Hamburg. I have been invited to this experiment from our colleague Moto Togawa. This experiment has been done in SQS beamline. The photon energy of the SQS from 500 to 3000 electron volt. And here we represent different order of the photon energy with the beam transmission. Here also we have the photon energy with the resolving power at different order of the beam. In the SQS, you can do many physics, but recently has been installed new instrumentation. It's called SQS EBIT. So also, if someone interested in this kind of study, he can apply for a beam time and perform experiment using electron beam ion trap. So the idea, one of the recent study has been done with the collaborator at AfLS. So we have 220 nanoseconds between the pulses, and each pulse is less than 25 femto second. So this allows us to study highly charged state even in very precise measurement. For example, here in the beamline, they have XGM1 and XGM2. This allow you to determine the photon intensity. It's called gas attenuator. And here you can attenuate for how much flux you need in your sample. For example, 50% of the beam or 80% and also 25 as you can attenuate. Here you have this like the sort of generating offline electron gun. You generate the highly charged ions in the central part of the drift tube 4, and then you have the photon beam from the X-field. So you can do a lot of physics. For example, here in the figure, I'm showing the overview from highly charged ions of krypton. Here we we generate highly charged ions of krypton up to krypton 26 plus. After that, we use synchrotron X-field photon to do photoionization. So the main interest of this study to do non-linear photoionization. So you have like photon from the X-field, you excite from krypton 26 plus to krypton 27 plus, which is fluorine-like atom. And then before the de-excitation of the fluorine, you excite again with another pulse from the synchrotron, and you have krypton 228 plus. So you have like linear processes from the synchrotron, and this is one of the advantages of the X-field. Here we show in the upper part of the overview the fluorescence yield of these highly charged ions, and below the mass spectrum of or the time of flight of the ion yield of different charge state of the krypton. This study has been also recently to be published soon in the BRL by Motorola. Here also we are showing the ion yield of krypton 27 plus and fluorine krypton-like and krypton 28 plus oxygen krypton-like. Here we have 5 characteristic peak from 1 to 5 and show each of these peak representing the ion yield spectrum. And from this study, I will not go in more details since this conference is not like mainly for atomic physicists, so I will just give a glimpse about this study. So mainly they are interested in the 3D and 3C yield, and they are like atomic excitation from some transition line, for example, from 3B1/2 to 3D 3/2 for the 3D, and from 3B 1/2 to 3D 5/2. This paper will be soon published and it will be available for the public. At the end of my presentation, I would like to thank all our collaborators from Max Planck Institute, my supervisor in CNR at Elytra, and my supervisor University of Camerino, and the staff from Elytra Synchrotron Dresden. And also we have national collaborator from INAF and also AfLS. Also, I would like to thank ICTV and HIT 2020 and Elytra for supporting attending also conference and useful. Thank you all.
Thank you. Thank you for a very nice presentation. Are there any questions for the speaker? I have just a quick question. Is that N3 plus ion, is that important in atmospheric sciences?
Exactly. So the main objective of this study, we are interested in highly charged ions. So there was some correlation of these highly charged ions. So there was like ongoing observatory like XMM and also now like James Webb. So this observation need highly charged data from laboratory to understand the collected observatory from this observatory. So for example, we are interested mainly in oxygen, carbon, and nitrogen because they exist in the interstellar medium. And we are manipulating this data in highly resolution measurement, which will enable like the observatory, and also there was also ongoing like another group working in the computational part, like theoretical modeling also.
Any other questions? I have another one actually about the N3 plus. So what are the channels for production of that ion, and what are the open channels for its fate?
In which sense, like in the...
So for you, I guess you presume you go from N2, right?
Same, exactly. So we started
and then you,
in the...
how do you get to N3 plus from there?
Exactly. So the idea to generate N2 plus in the central part of the EBIT, so you confine them in the central part of the EBIT. Maybe I can present with the picture. So here in the central part, you generate with the electron beam of the EBIT N2 plus. And then you photoionize with the synchrotron, then you will have N3 plus. Even sometimes you can even go further. In the X-FEL, for example, even you have delay time because the pulses are too fast, within below 25 frames per second. So sometimes even you are allowed to do nonlinear process. For example, you start N2 plus, you photoionize to N3 plus, and even you have enough time to photoionize again to N4 plus. So this even it open a lot of physics, neophysics, for example, to study nonlinear ions, for example. And this also opens the door. Normally, we work in the atomic physics in neutral mode, but even working with the highly charged ions, so you have like screening when you remove the electrons. That means you open the door again, like you are opening new periodic table of the atomic periodic table.
Right, and then so when the N3 plus ion forms, I imagine that. I mean, what's the spin state of that, and also what is the geometric and bond structure of that? So I guess there has to be a single bond to one of the nitrogen atoms.
Exactly.
Yeah.
Exactly.
And then I guess there's some kind of bond breaking process to relax back down to N2 and
exactly. Exactly.
Is there is there a forbidden surface in that process? Like it's a triplet surface forbidden, or so the N3 plus ion, is that a singlet or a triplet?
No, singlet.
Singlet. So there's no triplet pathway.
Exactly.
Gotcha. Okay. All right. If there's any other questions for the speaker. Well, let's thank him for a very nice presentation.
Thank you all also for hosting me for giving this opportunity for contribution talk. Thank you a lot for the organizer also.
Okay, and I don't think that the speaker that missed this time slot has come as yet. And so what we will do in this case is close the session and reconvene at 1200. That's 12 noon GMT plus 2, which is 25 minutes from now. And I see that speaker is already here. So let me actually make a co-host thing together. And so we'll reconvene at 12 o'clock with Dr. Lise Daniel, who is from the European Battery Hub, and will talk to us about that in 25 minutes. Thank you.
So, Lawrence, it's a break now?
It is a break for 25 minutes.
Okay.
Hi, Lawrence. Lawrence, are you there? Maybe step out.
Elise, if you want to go ahead and check your slides and your audio and everything, we could do that now.
Yes, thank you so much. So yes, I will try to share my screen. Mhm. Mm. Sorry. Yes. I have an issue with my screen. I will try again. Do you hear me?
Yes, I can hear you.
Okay.
And I did see your
Good.
screen. Yeah.
It's a horrible view. I don't know.
I can see your I
Yes.
can see your
Okay.
screen just fine. Okay, that's good.
Yeah, it's good. I think I can stay like this.
Yep, absolutely.
Okay, maybe I will.
We'll start in 7 minutes.
Okay, I will also put on my camera.
Okay, why don't we go ahead and get started? Our next speaker is Dr. Lise Daniel, and her co-authors are Cedrine Leonard and Xaver Brims, all with the European Battery Hub, which she is going to tell us about right now. Thank you.
Yeah, thank you so much for the introduction. Do you hear me well?
Yes.
Yes, okay, perfect. So first of all, thank you for the invitation to present this European Battery Hub. So I will present a short history and also give you a few words about the concept of this hub and how it operates. So as you mentioned, this presentation has been prepared mainly by Sandrine Leonard, who is the coordinator of the hub, and also Xaver Brems, who is the project manager for this hub. And personally, I am also involved as a principal investigator. So we are all working at CEA in France. So actually, what is a hub? So at the ESRF, after the upgrade, a new community access mode was launched by the ESRF in order to try to gather the scientists working in the same field in order that they can share knowledge, technology, beam time, and also beam time data and results in order to get to be more efficient and propose better science. So this aim is really to make this, to favor the collaboration between those scientists to produce great advances in scientific field. So the beam time distribution is quite new and quite different from the standard proposal. In the case of the hub, the ESRF grant a beam time, and the applicants decide themselves how they want to use this beam time, how they want to distribute the beam time. And what is interesting also is that with a hub, the beam time and the beam time request can be done on several beamline. So we can ask for several beamline, and we have an amount of around 18 shifts for each beamline, which is possible every 6 months. So I will give you more explanation after, but this is the global call from the ESRF to propose a hub. And what they are measuring, what the ESRF is expecting is a different point, for sure at a scientific level, by the publication of high impact publication, but also they expect some new tools, new methodologies, new equipment or setup that can be shared with the community. And also they expect some results about the organization of inside the hub with new way of beam time allocation distribution. So these are the three main expectations from the synchrotron. So why we have proposed a hub on the battery field? Actually, because the societal impact is very high. We know that the energy storage is now mandatory, and if we want to be efficient, we have to consider the different application and also to develop good batteries, the best batteries as we can. And so in Europe, we have a lot of projects of European gigafactories. We are facing these industrial challenges to be able to produce a lot of batteries because the demand is growing very fast, especially with the electric vehicle demand. We have to produce better batteries, not only more, but also better batteries, because we all want to have more autonomy, more lifetime for the battery, and also safe battery and low cost. And finally, what we need also to develop is more sustainable batteries, because we know that we have some compound like the PFAS that we need to replace. So the interest of batteries, but also the complexity, is that we can work with a wide variety of materials and targets, actually depending on the application, depending if you want to use your battery in a vehicle or if you want to use your battery to store the energy storage from a solar panel, you will not have the same batteries. And we can have, for instance, in yellow, you have all the lithium-ion chemistries that can be used. So some of them are already on the market, and some of them are still under development in order to increase the energy or the power or the safety. So we can see that the panel of materials is very large, already for lithium-ion, but also for other technologies like sodium-ion or potassium-ion or organic batteries. So we have a very big panel of chemistries that is possible. And we know that we will have the coexistence of different chemistries in the future. There is not only one technology, we will answer all the requests for all the applications. And so with all this variety of materials we have, it's quite complex to study the battery because the field is large. And also it is complex because it is like a living system. We have this transport of matter and this dynamic process inside the battery, which is also multi-scale. So it is complex because we are working, the lithiation process is at the atomic scale inside the crystalline structure. But depending on the primary particle size and morphology, and also on the secondary particle morphology and composition and so on, we will have different process and we can have different limitation. So it is multi-scale, and it is also creating some heterogeneity depending on the size of particle or the microstructure or the design, etc. The process will not have the same kinetics inside the particles and then inside the electrode and the battery. So all this mechanism can have some heterogeneous distribution, and that some of them can lead also to irreversible reaction, leading to aging of materials. So this aging can also happen at different scale. It can be at the crystalline structure scale, but also at the very macro scale, at the electrode level, where we can have some delamination, loss of contact, and so on. So to study this complex mechanism and complex system, we really need for advanced characterization. So as we have mentioned, this is we want to study the dynamics of the reaction. So during charge or discharge of a battery, we can follow the evolution of some property, like the evolution of the crystal structure, for instance. And so to do this operando measurement, the synchrotron facilities is very useful. And it is also useful because we can have this combination of high penetration, which can help us to study big objects like a real battery cell. We are able to see inside the battery cell what is happening at a very low scale. We can have this high spatial resolution because the beam size can be very, 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 very low. And so we can make this mapping with a very high spatial resolution. We have speak about this operando requirement with this high time resolution. It is something possible, especially after the upgrade of the synchrotron. The resolution or the time resolution is already improved. And finally, we have this high detection limit. So we can really find very, very small detail in a large sample. So the community working on the battery is very large, and we are facing some common challenges. So we are all working with battery cells with this electrochemical process, and we can use the synchrotron to collect a lot of data like spectra, pattern, images with a wide variety of techniques. And the challenge is to design the best experiment to get this high spatial and temporal resolution, to get this mapping of the key properties. Another challenge is to work on a representative sample. If we compare the real battery cell with a few micrometer cells, do we have the same behavior and so on? A third challenge is to make the correlation between the different characterization results we get with these different techniques at different scale. And finally, last challenge, but not the least, is all the data handling because we will generate a lot of data. And so we have to develop these tools to make the analysis more efficient. So our motivation and concept is really to accelerate the battery material innovation. And so by gathering together these scientific partners on the same battery field, we can share ideas, samples, data, analysis method in order to design the best experiment. So we have started first in 2021 with this pilot phase. So it was a pilot battery hub, first with ESRF and CEA, several teams in CEA, to try to establish the way of working inside a hub, how to collaborate, how to distribute the beam time, and so on. And then since last year, we have now extend this hub at a European scale. Now we are 7 European partners working all together with the same amount of beam time. We still have around 80 shifts per every 6 months. And so for the 3 years, we will have this beam time allocation. And we decided inside the hub, what are the proposals we want, what are the experiments we want to conduct for each round. And we have to deliver some annual report to ESRF, but the decision of the experiment we want to conduct is taken inside the hub. So with the pilot phase, we have developed some new community tools and standards. This is something which will be used, which is used in the European pilot hub, and that will go on and that will be shared with the battery users community. And so, for instance, we have developed some community tools and standards about the beam damage assessment. We have developed new setups with new in situ operando cells. We have also published some protocols about the data acquisition and also about the data analysis. So we are trying to propose this kind of tools, and this has been all published. And we have also demonstrated interest to couple the X-ray measurement with some modeling and also with sensing in the battery in order to get more data and also to establish more and confirm the hypothesis we can have simply with the X-ray measurement. So in the European Battery Hub, now we are focusing on 2 main topics for the batteries. First, solid-state batteries, mainly for performance requirement. We know that the solid-state batteries is the next generation, which is very promising, as it will increase the energy density and the safety of batteries. But we face some bottlenecks about ionic conductivity and stability of this the interface between the solid electrolyte and the electrode. And we are also working on the sodium-ion batteries, which are more mature. We have already some of them in the market, and they are very promising regarding the sustainability. However, we still have a limited energy density, so we really want to understand more the mechanism in order to discover new materials which are more performant and which can deliver high power and high energy. So we are focusing on these 2 topics with 80 shifts every 6 months. So it's approximately 1 experiment per month. And we are working on a 6 beamline, which in order to, so we have selected this 6 beamline because it can propose very complementary techniques at different scale. So it is very interesting to get information about the chemistry, about the crystal structure, the electronic environment. So the idea is to get the more information that we can on the same sample. So here you have a few pictures of the samples on the beamline. And for the partners, as I've said, we are now 7 European partners with CEA fundamental and technological research laboratories, CNRS, which is a French research center, ESRF, University of Chalmers, KIT, and also University of Beirut. So we have 7 PI for each, so one for each institute, which bring all complementary skills about batteries. And all these PI are also assisted with a co-PI. So in total, we are 22 scientific discussing about the experiment, how to design the best experiment to answer this scientific question every 6 months. So it is a very interesting discussion. And to make also all this experiment feasible, we are also relying a lot on the several PhD postdoc. And so we have counted around 50 users so far within our 7 institutes. So this is just a slide to show you the global objective by using these different techniques on the 6 beamline. We want really to address precise scientific questions and provide new results, new tools, new technical tools, and also new workflow in order to be more efficient in the process to discover new materials or new mechanisms. So we have established a governance inside the hub with a direct link between ESRF and the coordination team in CEA. And we have established an executive committee where each core partner has 1 representative. And we have determined what are the rights and duties for each level of members. So I will not go in details in all this governance because it is described in a document on the website. So if you need more information, you can go there. What is really important and new, thanks to this hub mechanism, is that we are discussing internally the proposal. Every 6 months, each member can come with its proposal, and then we see how together with the other hub members we can improve the proposal and collaborate in order to get more information in only one experiment. And finally, the executive committee inside the hub decide what are the priority experiments for each round. And then we send it for approval to ESRF, but the prioritization is made inside the hub. So we have established this proposal grading with also some kill criteria. For instance, if your proposal don't address the sodium-ion or solid-state battery, or if it is, we have defined these kill criteria in order to avoid making simple experiment which can be done elsewhere or which is not in the scope. And we have defined the key criteria. So really in the hub, we want experiment who belong to a workflow with a collaborative approach between different groups in order to get all these complementary skills together. We want to contribute to community tools and also publish the experiment and the results. So this is really the key criteria for the proposal inside the hub. So everything is described in these terms of reference document, which is available on the website. So I can now propose you a short summary of what has been done during this first year of the European Battery Hub. So since last year, we have run 15 experiments. It is more than 162 shifts. And so we have studied more than 20 different samples of sodium-ion or solid-state batteries. We are developing new setups, new cells. So we have 5 of them under development now. We have already conducted some experiment with more than 3 teams together on the same beam time and on the same beamline. So it is very interesting work. And we have started to publish or to communicate on the result with some poster or paper already published or submitted. So now we are also opening this, the hub to partners, especially in order to get complementary skills on 2 main topics. The first one is radiolysis and beam evaluation, and the other one is the machine learning aided data analysis. These are 2 main points where we think we can need more skills. So it is an open call for a partnership. And we will have some presentation of results and about the hub operation at the micro symposium at ESRF user meeting in February next year. So in the hub, we are working on these 2 chemistry, solid state battery and sodium ion batteries at all the scale. Really, we need to have this correlation between all the mechanisms we can see at different scale. So we have different setups depending on what type of samples and what are the mechanisms we want to investigate. And today I will give you a few examples of ex situ experiment and also experiment done with small cells, which are below a few millimeters of diameters. But we are also conducting inside the battery hub some experiment on a real coin cell or pouch cell or cylindrical cell, as you can find in the market. So these are these are very recent results. So from this last year. So this is one example of an experiment conducted by several of the partners inside the hub. You can see all the logos of the partners involved. So they all want to study the anionic redox mechanism in this sodium ion cathode material. And the goal is really to have more information about the participation of oxygen in the charge compensation mechanism at high voltage, because we know what we expect is the contribution of the nickel and manganese in this particular case of the metal part, but the oxygen is something which is still open question. Does it contribute, how it contributes, and so on. So for this study, experiments have been conducted on ID20 by coupling the X-ray emission spectroscopy with the X-ray Raman scattering to get information on all these elements, nickel, manganese, and also oxygen, and to follow the oxidation state of the material in order to better know what is happening inside. And for instance, in this case of this material, we have confirmed that the oxygen is contributing to the electrochemical process at high voltage. So we have compared some material at the pristine state and also at the fully charged state in order to see how what are the contribution and what are the oxidation state of the different elements. So this is something which is published or will be published. I don't remember, but it is very, so we have studied different composition of material in order to check if this oxygen contribution can be seen all the time, or is it depending really on the composition and structure of the materials. So still another example on the cathode material for sodium ion. Here, it's not the evolution of the structure during the sodiation process, sorry. It is more the evolution of this structure during the synthesis process. So this material, depending on the temperature, for instance, of the synthesis, we will generate different type of phases. And the idea is to find the best one in terms of electrochemistry. And so this study made especially by Beirut University has used the microbeam X-ray diffraction at ID 13 in order to have a mapping of the different phases inside the particles. And so it has been seen, we have this very precise mapping for all the particles, even if it is quite small particles. And so we can see this, we have seen this phase transition from P3 to P2, which takes place from the outer shell of the particles towards the core of the secondary particle. So this is something which is interesting to know in order to adapt the process for synthesis of battery materials. Another example, so now it is focusing on solid-state batteries, in which we will have, we aim to use the lithium metal directly as an anode. But we know that the lithium plating and stripping will generate some heterogeneous structure, a 3D structure of lithium deposit, which is quite difficult to control and which can lead to some dendritic shape, which can be then dangerous for the batteries because it can create some short circuits. So we want to find a way to characterize first the lithium structure to finally optimize the process to avoid the heterogeneity and the dendritic formation. So this is done with a mini cell where the diameter of the electrode is below 1 millimeter. And on ID 16B, we can make this nanotomography and follow the morphology in a 3 dimension of the lithium. And what is under development now is to, with the same cell, to add some pressure also, because we know that the pressure will play a lot on the morphology of this deposit. So this is, for instance, something under development, which can be then used and useful for all the scientists who want to study the deposition of metallic lithium or metallic sodium, for instance. So this is something which is developed now by CEA and Chalmers, especially in the hub. I will then show you an example of another cell. So this is a cell where the diameter is around 3 millimeters. And we have studied another cathode material for sodium-ion batteries. So this is another family, which is Prussian blue analogs. So these materials are very promising because they are easy to prepare and they contain it is quite low cost and could be competitive to lithium iron phosphate in a lithium ion battery. However, we know that these materials are very sensitive to the air. So if we want to process this material in quite simple environment, we have to know exactly the kinetics of this transformation if we expose it to ambient air. And so we have conducted experiments with a specific setup where we can follow the evolution of the material structure in the same time as we flow the sample with our a controlled humidity. So we have followed the rehydration process and we have seen that the transition is occurring in around 20 minutes. So it is quite fast. If we want to process the material, it's quite difficult. What has been seen is that this transformation is irreversible. We get a monoclinic phase, which is different from the initial one. And what is interesting is that this, this rehydrated form is more performant in terms of electrochemical properties than the initial one, which is hydrated at the initial point. So it is still below the dehydrated phase, but even if we have this rehydration process, it is not so detrimental for the electrochemical performance. So this is something we want to investigate more, and by controlling, by testing different humidity level and also particle size and so on. So as a conclusion or a summary, with this new hub, with this new way of collaborating and have access to BeamTime, we have created this community and with new community tools, because we are sharing all our new setups, cells, and we are also sharing new ideas and experiments. So this is very interesting, because by collaborating together, we can optimize the use of BeamTime and perform right experiment and avoid making redundant experiments done by individual group. So it is a new model for scientific cooperation and training. So what we have learned up to now is that it is very useful for all. But for that, we want to emphasize that the sharing is needed, but it is not so easy, because we have to establish some rules and also some tools to share, for instance, the data or all the results in general. So this organization and working on common goals is really a key. And also the involvement of the synchrotron scientist, because if we want to build the best experiment and take also into consideration the beam damage evaluation, for instance, we have to design the experiment with the synchrotron scientist. So this idea of hub is something which is more and more coming in the mind for other synchrotron also, and also for neutrons. So Sandrine Léonard and all the other contributors have published this paper on this meta infrastructure to accelerate the battery innovation in Europe. And I would like just to show you a few pictures of the last experiment we conducted last month at ID31, where we have people from the 6 different groups from the hub cooperating together on the same beamline on the same topic. So they want to study the sodiation mechanism of the anode material, so the hard carbon. And so we have conducted a 2-day tutorial before the experiment in order to align all together on how to make the cell, how to conduct the experiment at ID31 and so on, in order to be able then to compare all the results on the different samples we have studied. So this is just a summary slide where we see all the different challenges we have to keep in mind as soon as we want to address our scientific question. So it is everything that I mentioned already about the representativity of the samples, the reliability and reproducibility, but also about the beam interaction assessment and also the data handling. These are all these challenges we have to keep in mind as soon as we want to make the one experiment. And so we have now this website, which is now working and which is available. So you can have all the information and also access to the different papers we have already published in the website. So you will see how we can work, who is involved, and so on. And so if you want to be a partner, it is something which is possible by bringing some complementary skills, especially, but also some tools, resources, and new scientific case. It is something which is really interesting to discuss in the hub. So if you have any question, you can go through the website or also contact directly Sandrine Léonard at CEA. So I would like to thank you for the invitation to present the hub and also for you to attend this presentation. Thank you. So if you have any question, I will be pleased to answer, to try to answer to you.
Okay. All right. Well, thank you. Thank you for a very nice talk and overview of the hub. Are there any questions for the speaker? I have so you have, the hub confines itself to the sodium ion battery, which is interesting. I mean, are you open to other types of batteries? I mean, I don't know what else is out there, but I do imagine that it is possible using artificial intelligence and machine learning to design, quote unquote, the perfect battery. If you could envision like the correct, maybe metal organic particle or something like that.
Yeah, you're totally right. Yeah.
Yeah.
Yeah, it was not so easy to select chemistries when we have proposed a battery hub, because depending on the application, the type of battery, the chemistry inside the battery would be different. So depending on the needs, you have to choose the best chemistries, and you're right. We can find the best composition or the best coupling of anode, cathode material, electrolyte with the artificial intelligence. The main difficulty is really to know what are the criteria we have to consider, because as we have so many materials chemistry, so we can play on the composition, the microstructure. We know that it plays a lot about the process. Yeah, there are really a huge panel of possibility, and more we have some AI tools to guide, especially on, for instance, I don't know about if we want to apply a coating, for instance, on particles, what would be the ideal thickness or the ideal composition if we want really to suppress one specific mechanism. So AI can really help us as soon as we identify really one bottleneck and the corresponding criteria that we can, where we can play on. And about the other chemistry, so all the scientists involved in the hub are also studying other type of batteries, and so they can apply for a standard proposal on other topics or other beamlines.
Yeah,
it is something which is possible also.
Mac, you have a question?
Yes,
I
please.
think it was the same. My idea was if you need to optimize the best battery, maybe with what's the abundant material to use, or what's material available. I think they deal also with the life cycle of the battery, and I think it's what I was planning to discuss, but she already said that AI can help designing this kind of battery.
Yeah, and we are also working on developing new methodology to assess all the life cycle assessment and also the environmental impact, because it is some criteria which is not the first priority one for some application, but it is coming more and more important. So we have also to know how to assess those kind of parameters and impacts in order also to, for instance, for the PFAS, it is something which is commonly used in all the batteries, but now we have to replace it, mainly considering this environmental impact. And we are not focusing only now on the performance of a battery. It is, yeah, it is evolving a lot.
I think
What
your hub is really shaping the way if should the African light source be operational, how can country in Africa can collaborate on common projects. I think Laurence already mentioned the center of battery in Lubumbashi, but no one know what they are doing, so they don't communicate, and hopefully we hope to learn from what we are doing. Yeah.
Yeah. Actually, I tried to communicate with them, but my French was not good enough to really get into a conversation at that very high level. I have to practice that more. But I wanted to, I think with the European hub, there might be, I think I was thinking in terms of decoupling the chemistry of the battery to the techniques of photon interrogation of whatever battery people can develop. So like Mac in his talk talked about a material that may have some electrochemical properties that might be interesting to try in a battery, but it's not a sodium. It was iron. What was the material? Iron, niobium, and what other element was in that material you're looking at, Mac?
Cobalt also is already used in battery, I think. Cobalt, uh, uh, nickel also, you said nickel you
Yeah,
need
nickel.
for, yes, in place of manganese, for example. I
Right.
think alternative material can be different simulation, different tests, and try to see the optimal solution and
Right.
the sustainable one.
So there might be a mechanism for collaboration, maybe not necessarily through the hub, because the hub wants to do sodium ion.
Yeah.
But at least
actually for up to until 2027, the focus is on these two chemistries.
Yeah, and that's fine. But I think where, like, as far as Africa is concerned, I think the techniques of and access to the beamlines is where we might want to come in. But we can discuss that further into the next year, because I don't know if you saw the link in the chat to this center in Democratic Republic of Congo. At least I don't know if you saw that link. But it's still in there, I think. About a center that's in the Democratic Republic of Congo. And like Max said, we have to nail down exactly what they are doing.
Yeah.
And see if there's some opportunities there. Are there any other questions for the speaker? We have a little bit of time. I think our next speaker is not yet arrived, and not to tell you her whole story. I don't know if she's going to be here.
No, I just talked to her, Lawrence.
Yeah.
She said it's 1 o'clock. Then I say yes. So I think she will log in before 1.
Right.
Yeah.
So I apologize because at least I started you off 15 minutes early because the thing that was pushing everything by 15 minutes didn't actually occur. Like,
no problem.
The plan was earlier today. So
yeah, no problem.
So the plan that was the plan did not go as expected. So we have time to either take a break, or if you have more questions for any of the speakers, or any general discussion, or you can go for tea break.
Yeah. I have one quick questions to the excellent presentation. Yeah, this is Philip. I want to know, have you been working with any of the African country researchers in the area of battery?
I am not aware of such kind of collaboration, at least for a CEA side. Maybe some of our colleagues in the hub from the other institute have some collaboration. I am not aware about collaboration with some African collaborators, but it is something maybe to build.
Okay, because I know some African researchers, about 1 or 2 from different countries, who are working on the battery. Yeah, so that's what I was asking for now. Then 2, did your organization perhaps have a little mobility funding for something you are proposing for somebody from our continent where we know that a bit financial constraint in terms of the synchrotron? Because I believe the essence of the African license is to try for African researchers to be actively involved in data analysis and the hands-based equipment for the synchrotron. So I know that collaboration fine can be done, but I'm just trying that is there something like we are proposing so that Africa also can sometimes be there to witness how the analysis being carried out at your facility.
It is something I have to ask to the consortium. I don't know now if we have such kind of funding possibilities. Maybe at ESRF they have some program. I don't know. I will ask to at least ESRF and within the consortium if we have. Up to now we didn't face this case. So
Okay.
no.
All right. Okay. I think that's just my answer. Okay. Thank you very much. Yeah.
Thank you. Thank you so
thank
much,
you.
all.
All right, so we have a little 14-minute break, and we'll start with the next speaker.
Thank you. Bye.
Thank you. Bye-bye.
Okay. I think if the next speaker is there, you can upload the slides. Then we wait for a few minutes before she starts. Yeah. I think she's supposed to be there. Yeah.
Okay.
Yeah. I think she's there.
Do I see her? I don't.
Yeah, I can see her. Yeah.
Oh, but
Dr.
okay. I got it. Make co-host.
Yeah.
That's
Give
her
her
right there.
Yeah.
Okay.
Yeah. I think that's fine.
Okay. Good to see her. Good.
Yeah. Okay, Dr. Adu, you can try to upload your slides. Then before we introduce, you can share your slides.
Fantastic.
Okay, you guys can see this, right?
Yes.
Thank you.
Okay, Philip, you can chair the session. I'm going to make a quick tea run. I will be right back.
Okay, can we start now, or what do you feel? It's 10 minutes, or we should wait till 10 minutes?
So somebody run to get some tea, right?
No, I'm the one going to start it. Going to check the session. Okay. Let me just give you a few, maybe 10 minutes, then we start.
Sure.
All right, colleagues, I think we shall start because if you look at the time, our next speaker is supposed to start at 13:00 here. So I think we are good. So our next speaker is going to be Dr. Aru Natanashata from the Synchrotron Light Research Institute in Thailand. So she will be talking on the bulk electronic structure of lanthanum saboride by hard X-ray angle resolve photoelectron spectroscopy. So the floor is yours, Dr. Aruna.
Thank you, Dr. Phillips. So I am Aru. That's a shorter version because my real name is extremely long, as are the Thai people. The topic, as was announced already, which is the bulk electronic structure of lanthanum hexaboride or LAP6 by hard X-ray angle resolved photoelectron spectroscopy. So we did the experiment in several places, in several synchrotron places in Spring 8, and the one that we locate out my former group, which is Fatley group, is at the ALS. So this is a nice view from the balcony right in front of the ALS. You can see the Golden Gate Bridge. And before I go it doesn't want me to. Okay. Before I go any further into my talk, I would like to thank this person, my late advisor, Professor Charles Fatley. I think people in the synchrotron and AfPS fields know him very well, that he is a pioneer in X-ray photoemission spectroscopy and also in hard X-ray as well. He passed in August in 2019. So this topic was never given anywhere due to his passing, and then right on we had the pandemic of COVID-19 hitting the world. So let's see what my talk today is gonna come. So the outline of this talk will be the introduction. So I'll let you know I'll introduce you to the sample that we use and why do we use them, and then the method of the experiment that we use, results and discussions, I'm sorry. And the last one will be conclusion and future work. I am so nervous here. All right, introduction. Number one is the AfPS, which is X-rays, photoelectron, spectroscopy. What actually is AfPS? AfPS based on the effect that we call photoelectric effect, which was discovered by Einstein, and that was the Nobel Prize that he was awarded. So we shine the light, in this case, X-ray, onto the sample, and these X-ray or photons will knock electrons out of the sample. These electrons will carry out the information with them, and we will have analyzer, which is the energy analyzer. We'll take in these photoelectrons and give us some curves or some results. So why do we do hard X-ray? if you see this that graph of the inelastic mean free path versus photoelectron kinetic energy, you can see that if we want to go deeper into the surface, we need the X-ray to be in the hard X-ray region. Or this is from TPP in 2011, which we still call this section hard X-ray. But nowadays, this part turned to be tender because fourth generation synchrotron can push the for the X-ray energy to be higher than this. So now we have soft X-ray, tender X-ray, and hard X-ray. So lab 6, why lab 6? Because this material has been studied for more than 4 or 5 decades, and people know almost everything about it. But why our group back then, or Chuck, was interested in it? I'll show you later why. But here is the real sample, which is it's a commercial one that we purchased. And this is the crystal structure of the lab 6, which is a simple cubic of lanthanum atoms and the octahedral of boron atoms right in the body center of the simple cubic. And this is the experimental geometry that we use. The data for this experiment was collected at beamline 15XU X-ray undulator from the Swing 8. And this is the setup that we use. So very glancing angle, and the surface orientation is 001. So we use two, well, not really two, but yeah, okay, two methods. So XPS, hard XPS or AfPS, and the second one is hard X-ray angle resolved photoemission spectroscopy or AfPS. So they're the two. This is the result that we get from the survey spectra, just to see what do we have roughly in our sample. So we see all the lanthanums are there. Boron, which is only one peak, is there. We have carbon, oxygen, and fluorine as surface contamination. So no other, no other contamination substances. So let's go further into the term of the surface contamination. Going back here, you can see that we have oxygen, we have carbon, we have fluorine. But after we flashed with the current up to, if I'm not mistaken, 1800 Celsius, so the fluorine is gone. We only have oxygen and carbon left. And we're comparing these two as we normalize the peak against the lanthanum 4S peak. You can see that this is carbon, then this is oxygen. The blue line is with the lower photon energy, which is 3,200 and the red line is 5900 eV, so higher photon energy. So surely that we can see more contamination on the surface, which is with a low photon energy than the higher one, because the higher photon energy will go deeper into the surface, so we can actually probe the bulk. You can see that the carbon amount is lower with the higher X-ray energy. And this is the main of the talk today, which is the recoil effect. I forgot to say that if you have any question, you can stop and ask me at any time that you would like. I'm not gonna say that I can answer all of them, but I'll try. Okay, let's come back. So with the core levels and the recoil effect here, what is the recoil effect first? It's when the atoms, or not in this case, when atoms got hit by photon. So when the electrons are coming out, it loses its energy in the form of the kinet, how would I say? It will so how would I word this? So the atom will shake and absorb the extra amount of energy. So the recoil effect will occur with the really light atom. So in this case, we have lab 6, which is lanthanum, a really huge D-band metal, compared to boron, which is extremely light, a small atom. So when we hit that with the high photon energy here, almost 6,000 eV, you can see that with the lanthanum atom, there's nothing move at all. Two peaks are in exact same positions. But if we look at boron 1s, there's something happen here. So with the higher photon energy, you can see that the peak of boron 1s shifted to the higher binding energy, but the one with the lower energy is still there at the position that it should be. And in this case, this red line here is not any chemical shift or any contamination or any oxidation state of boron. It comes from the recoil effect, which in this case, the photon energy transfer into the motion of the atom due to the conservation of momentum. So the loss of the electron energy is called the recoil effect. So here is the formula for the recoil effect. And we got the result to be to agree with the theory. Okay. And this is the AfPS result. So AfPS is hard X-ray, but hard X-ray angle resolved photoemission spectroscopy. So let's look at A first. All these, this one is collected at the photon energy of 3200 eV. What happened to the 6000 K, right? Because previously we have two energies that we collect the data, and what happened to the higher photon energy. The higher photon energy doesn't show us anything at all because the photon energy is too high, even though with the cooling of down to 30K, it doesn't help with the phonon effect. So it smeared out everything. We cannot see anything at all in the 6 keV, but the 3200 EV photon energy, we can see the pattern. This is the raw data. And then we use Boswick program to normalize the density of state and the contribution from the XPD. So we can still see that here's a band and the Fermi level is at 0 eV here. So we have our group in Europe help us with the two calculation here, which the result that we got agrees very well with the theory. And this is showing the tilt just a little bit because we didn't align the sample like exactly perpendicular to the analyzer. It's off by about 0.6 degree. So that's why there's a little tilt there. And the future work, we were gonna study more of the rare earth hexaboride, but then COVID hit, so everything got stopped or canceled. And so I do hope that I will get to work on these materials again. So this is it for this talk, for this first set of slides. Do we have any questions?
Okay. Okay. Lawrence, you want to say something?
Just a quick question. So the sample itself is in a solid phase. Is it
Yes.
Is it a thin wafer or
It's a single crystal.
single crystal? Okay.
Yes.
And the recoil effect, is that through all bonds, or is there a specific mode that is I guess recoiled while some modes sort of remain static?
It depends. It depends solely on the mass of the atom and the kinetic energy of the photon. So, am I answering the question? It doesn't depend on what polarization it is, just the energy and the type of atoms that it hits.
Okay.
Okay. So I do have one more set of slides that I would like to present. So that was the work that I did with Chuck, and this is the synchrotron light source in Thailand. So let's hear what we have and what we can do here. So, oops, it's in Thai. SPS1, that's what we call it. We have 10 beamlines and 12 experimental stations. So this top view of it, the beamline. So here it is, PES and PEM. That's where I work. So we have 10 beamlines, 12 end stations, both soft and hard X-rays, and also IR spectroscopy as well. But for XPS, we only have soft X-ray. That's an undulator.
Do you want to be showing us a different set of slides now? Because what I see is the last slide of your first part of your talk.
Oh my God, I'm so sorry.
Oh, that's okay. I was take your time.
You didn't see it?
I see the thank you slide from your first part of your talk.
Oh yeah. Let me do this.
Yeah.
Let me do this again.
There you go. I think that's what you want to show us.
Oh my God.
Yeah, so you're on the third slide of this.
Oh yeah, because I changed and I thought you guys see it. Okay, let's start from the top.
Thanks.
Okay, here. Thank you so much for letting me know.
Okay.
Here, so 10 beam lines, 12 end stations. Here we have both soft and hard X-ray. We have IR. We have X-ray lithography. We have a lot of X-ray absorption beam lines with both hard and soft X-ray. And XPS and PM, they all in soft X-ray region with the undulator. Oops. So we can categorize our beam lines into 6 groups. So imaging, which is X-ray tomography. The elemental analysis, we go for XRF. Chemical state, XPS and XAS, of course. Molecular structure, we have IR, which we have both standalone and synchrotron IR. So for the fabrication is the deep X-ray lithography and periodic structure. We have a lot of them as for example, SAX, wax, XRD, and protein crystallography here. So these are the work that was done here on rice and mice bones during, with osteoporosis. We did the mask, which was from silk during the COVID pandemic, which is better than regular fabric masks. And this is the XRF beamline that is not only for some weird sample, but we get to work on some ancient coins and ancient gold pieces that were found in several places. And once we use RF to find the amount of the relative amount of elements of each piece, so we can put them in groups and try to locate back where it was originated and where it was brought across the sea to somewhere else. And this part is the I have no idea how this one is called even in Thai, but it floats in water, and we can see that it absorbed heavy metal into its stems and leaves. Molecular structure we do on both lipid, protein, nucleic, and carbohydrate. And this is the lithography. So we do microfluidic devices and MEMS, but lately when 3D printing come in, the lithography has likely been used. Another periodic structure again. So XRD, SWAX, SAX and WAX, and XAS. And the last one is this chemical state for XPS and PEM. So this is also from a tree, if I'm not mistaken. So we'll come back to this end station that I work at. So we do have two analyzer. This one is VG, and the setup is for C-enter R4000. So this is the only beamline that can do NICSAF and also XPS as well. So we did a lot of NICSAFs when we have projects with graphene and DLC to confirm that what we fabricated is in the state that we want. So, and here is the new one, which is SPS2. I don't know where the topic went. This is SPS2. By the end of this year, so it was supposed to be able to start building the project, which is the 3GeV synchrotron between third and fourth generation, which with full capacity, we're going to have 22 beamlines. But the first phase is 7 beamlines. So after the construction and the commissioning supposed to be in only 7 years. So in the next decade, we'll get to relocate from SPS1 to SPS2 to serve more people in this region. So I do hope that after this talk, I will get some contacts from scientists and researchers in this area to come to participate or conduct experiment with us in Thailand. So do we have any questions?
Okay, thank you very much. Colleagues, if you have any questions, then we can ask the speakers. So from my side, in total, you have how many do we have now in terms of the beamline for SIR?
Can you please repeat the question?
Yeah, how many beamline in total do you have in your facility?
How many beamline total right now?
Yeah.
12 beamlines. We're building another one, so there'll be 13.
Okay.
And that's an SPS1, right?
1, yes.
So then you're looking for authorization to start building SPS2 by the end of this year or the next year?
Should be the end of this year, but it got postponed. So hopefully by the end of next year.
And so the idea is to build a whole new storage ring, and then I guess some beamlines will
So to build everything, Linac might be a turnkey one, but Booster definitely in-house. And storage ring is in-house as well. And all the hutches and utilities, also everything made in Thailand except those beamlines, parts of beamlines. So SPS2 is aimed to build people as a so not to just buying things and import them and put them together, or to do a turnkey project. So we want to build our people to get to know, get to learn about synchrotron, and build our and not to build, but to support the domestic business.
How many of the 13 beamlines in SPS1 will make their way to SPS2, or are you just going to just start with a new everything?
As far as I know, only one beamline will make it there. And the rest we will build new ones.
It'll be interesting with that. What can be done with the components that are left behind?
Yeah.
That's still not. The decision is still not solid on what exactly they're going to do with them, because we are going to be relocating to the new location in the Eastern Economic Corridor of Innovation, about 6 hours from our location now. But we will be there with other large scientific infrastructures. Almost all of the science institutes inside Thailand will move there. So build there as an innovation hub.
Understood. Yeah.
Yes.
Maybe
Philip, I think Mac has a hand up.
Yes, my preoccupation was about the project is full funded by Thailand, or we have some partner out of Thailand?
Can you please repeat your question?
I mean, the project, the new project SPS2 is fully funded by your government, or you have different partners out of your country?
Funding, right? In our case, we have funding from Japan. Yes. Like big other large infrastructures, like the SkyTrain in Bangkok, that was also funded by Japan as well. So it's a low interest loan from the government of Japan to developing country to build what's supposed to be built, but we don't have the large amount of fund to use it at once.
Okay, I see.
Any other questions? Any other questions? I did just a side talk. Lawrence, I think maybe African licensors can try to ask about what they are going to do with the remaining component.
Yeah, for sure. And also, I guess have a lot of design decisions been made for SPS2?
Yes.
So we can learn. You can still learn from what's been done, because I think the field, these things advance by looking to see what has already been done and either copying it or taking the next step.
All right.
Okay. Well, thanks to the speaker. I know I just want to express my thanks. I know that it was a challenging day, so thank you for coming.
Thank you very much for having me, and thank you so much for accommodating me with the trouble that I have right now. So thank you. Really appreciate it.
Okay,
All right.
thanks. Have a good day.
Bye-bye. Have a
Bye-bye.
good day.
So I think we are now on break. Till when are we coming back? Let me check the program. I think we are resuming on the at 2 o'clock. That is in 30 minutes time. So we are now on break. We go for a break. Then we come. We resume 14:08.
Are you chairing that session?
I know.
No.
Yeah, I wanted to talk to Kuda.
I mean, I could. I was.
Okay.
I asked because I was going to take a break that might take longer than 30 minutes, but I can put that off.
Okay. All right. Thank you very much.
Okay.
Okay. All right.
Is that Yosuke Senju? You can test your slides and audio and everything now. And we'll start in about 5 minutes.
Okay. So let me share my slide. Can you share my, can you see my slide?
Yes.
Okay, thank you very much.
And let me just check to see if any of the other speakers are here. Ibrahim? Yes.
Yeah, good afternoon. I'm available.
Okay, so we stay on time. You'll start in 2:15. Brian, are you here? Don't see Brian as yet. Radia? Professor Radia Batashi? Professor Tebaha? Do not see as yet. Takarayuki? Yes, I see you.
Yes, I'm here.
Okay.
Can I test?
You can test, yes.
Can you see my PPT?
It's coming, yes. Okay.
Okay, thank you.
So we'll start in 4 minutes. Okay, let's start this session. And our first speaker is let me make sure I pronounce it correctly. Yosuke Senju.
Yes.
So yeah, please go ahead and begin your talk.
Okay. So I'm Yosuke Senju from Okaina University, Japan. So today I would like to share so about the phosphorylation of the bar domain protein paxin to regulate caveolar morphogenesis and endocytosis. So so caveola is one of the lipid microdomain at the plasma membrane, and caveola is formed by the caveolin, one of the molecules present at the plasma membrane, and the caveolin forms the homodimers and generates the membrane invaginations at the caveola. So here I show the beautiful images of the caveola at the plasma membrane, which is observed by the quick freeze deep etch electron microscopy. So caveola is a highly dynamic membrane microdomain, and that can be observed by the total internal fluorescence microscopy. So we use the microscopy to observe the caveola at the plasma membrane, and we found that they are highly mobile plasma membrane structures, and also we found that they appear and disappear at the plasma membrane. So caveola is a highly dynamic microdomain at the plasma membrane. So this caveola is regulated by one of the lipid binding protein called bar domain proteins. Here I show the structure of bar domain protein, which is solved by the X-ray crystallography at the synchrotron in Japan. So the bar domain proteins form homodimers, crescent-shaped homodimers, and it sense and generate membrane curvatures. So generally, bar domain proteins bind to the negatively charged phospholipid through the positively charged amino acid and generate the membrane curvatures according to the curvatures of the protein structures. So we previously found one of the bar domain protein called paxin-2 localized at the neck of caveola and regulate the formation of caveola. So we further found that this paxin-2 is phosphorylated one of the kinase called the protein kinase K, and we found that the phosphorylation site of paxin-2 in the protein structures. Here I show the domain structures of paxin-2, and the N-terminal region has a bar domain which sense and generate membrane curvatures, and paxin-2 has a C-terminal SH3 domain which bind to the dynamic GTPase, which catalyzes the membrane fission at the caveola at the plasma membrane. Then paxin-2 expressed in HeLa cells, one of the mammalian cells, it generally generates the membrane invaginations as I indicate by white arrowhead. However, when a homosympatric mutant of paxin-2 is overexpressed in the HeLa cells, it stops to generate membrane invaginations, which indicates that the phosphorylation of paxin-2 negatively regulates the generation of membrane curvature and presumably regulate the caveola formation. So we then next treated HeLa cells, mammalian cells with the PKC activator BMA or PKC inhibitor BIM. When cells are overexpressed with the PAX2 wild type, they generate membrane invaginations. However, when cells are treated with PMA PKC activators, PAX2 stop to induce membrane invaginations. On the other hand, when cells are treated with PKC inhibitor BIM, the cells start to generate membrane invaginations again. That means that the phosphorylation negatively regulates the generation of membrane invagination and presumably the formation of the caveola at the plasma membrane. So we then try to understand how phosphorylation of PAX2 regulates the formation of caveola at the plasma membrane, and we wonder whether the membrane binding might affect the membrane binding affect the formation of caveola. So we used the liposome co-segmentation assay. So this is a very simple assay to identify the lipid binding proteins. So we first mix the liposome and protein and subjected to the ultracentrifugation. So after the ultracentrifugation, we separated supernatant and pellet, and this pellet contains the protein-bound ribosomes. So it is easy to understand, to identify the lipid binding protein using this liposome co-segmentation assay. So I show the result obtained by this liposome co-segmentation assay, and phosphorylation of PAX2 somehow reduce the membrane binding of PAX2, as I show here. And P means pellet and SN means the supernatant, and P contains the protein-bound ribosomes. So the phosphorylation reduce the membrane binding of PAX2. We also carefully we also carefully investigated whether the phosphorylation might also affect the protein structures. So we first performed analytical ultracentrifugation to understand whether the phosphorylation affects the protein dimerizations. So as we can see here, the PAX2 wild type and phosphomimetic mutant both form the dimers, which is investigated by analytical ultracentrifugation. So the phosphorylation has almost no effect on the protein dimerization on the PAX2 protein structures. Then we also investigate the effect of protein conformation by phosphorylation using the Sachs experiment. So both wild type and phosphomimetic mutant, the phosphomimetic mutant of PAX2 has no effect on wild type conformation observed by the Sachs experiment. So the phosphorylation also has almost no effect on the protein structures. So finally, we studied the effect of phosphorylation on PAX2 interaction partners. So we investigated the interaction of PAX2 with dynamin-2 by ITC. So dynamin-2 is a GTPase which binds to the PAX2 through PAX2 SH3 domain, and dynamin-2 catalyzes the membrane fission at the caveola. So as we can see here, that dissociation constant KD value of the both wild type and the host-mimetic mutant has almost the same value, which indicate that the vaccine 2 and the host-mimetic wild type and host-mimetic mutant both have almost the same affinity to the dynamic 2 TTPS. So this result suggests that vaccine 2 host relation rather regulate the membrane binding, but not so much effect on the interaction with the dynamic 2 or protein structures. So let me summarize what we learned here. So what we learned through this project, that we found that the vaccine 2 regulate the caveolar microdomain formation, and this vaccine 2 is phosphorylated by a protein kinase C, PKC. So we found the phosphorylation site of vaccine 2 by PKC, and this phosphorylation rather regulate effect the reduce the membrane binding of vaccine 2 at the plasma membrane, but they have little effect on the protein structures nor interaction with the dynamic 2. So reduction of the membrane binding of phosphorylated vaccine 2 suppress the caveolar formation and also regulate the caveolar endocytosis or buffering membranation at the plasma membrane, which would be very important for the physiological function of caveola of the plasma membrane. So thank you very much, and I'm happy to take any questions.
Thank you. Are there any questions for the speaker? Let me ask a sort of a quick question is, what is the size of these liposomes here?
So here, size of the liposome is around 100 nanometer.
Mm-hmm. And is it delivering something to the cell nucleus or something? Is it what's inside of it?
Sorry, I couldn't hear you well.
What is inside of the liposomes? Is it and what happens to is the liposome delivering something to the cell nucleus, or is it just trafficking some membrane proteins?
So first, the size of the liposome is around 100 nanometer, and it also can be possible to deliver liposome to several organelles in the cells. For example, this can be also used for the drug delivery systems.
It's interesting. Are there any other questions for the speaker? And what was the type of electron microscope? Did you have to make a model of? So you use an electron microscope or fluorescence microscope?
We both use the fluorescent light microscope and also electron microscope.
Gotcha. Okay. All right. Well, thank you very much. I don't know if there's any other questions for the speaker, but let's give him a round of applause and a thumbs up.
Okay.
And thank you for coming to our conference.
Thank you very much.
Mm-hmm. The next speaker is Ibrahim. Yes. And I think
yes, good afternoon. Yeah.
You can share your screen and start your talk.
Thank you. Is my screen visible?
Yes.
Okay. So, good afternoon, everyone. My name is Ibrahim Hamza Mishanu. I would like to first appreciate the organizers for giving me the opportunity to present my work. So this was actually part of my MSc dissertation, and it was done at the Butker Institute of Nuclear Physics. You can see the title is Longitudinal Beam Dynamics using strike camera imaging. Before I start, I would like to emphasize on the importance of diagnostics in accelerator facilities. In order to provide optimal beam to the user experiments or for collision experiments in high energy physics, there is always need to know the states of the beam in the accelerator. So next, I would like to give an overview of the facilities used. The first, it's called the VEP4M, which is a lepton collider. It was built actually for high energy physics and precision experiments. It operates with an beam energy of around 4.7 GeV. At the same time, it can also provide synchrotron radiation to user facilities due to the high intensity of the synchrotron radiation, like due to the energy of the beam. So in this facility, we use the synchrotron radiation from the bending magnets to perform the beam, the longitudinal beam measurements. The second facility, it's the Novosibirsk free electron laser. It is based on energy recovery LINAC with 3 lasers mounted on it. The first, it's in the range of terahertz, while the second far infrared and the third, it's near infrared. It's a low energy beam machine around 42 MeV. So the synchrotron radiation is very low. Therefore, we decided to use Cherenkov radiation for this. Next slide. Then the diagnostic tool used for this is, is a strike camera, which allowed us to take time resolved images of the beam. So it has a resolution of less than picosecond with dead time between snapshots between 300 nanoseconds to 0.5 nanoseconds. Strike camera, the principle it is not that complex. It takes a light pulse, convert it to electrons, and then the electrons are now being swept according to their arrival time, meaning that faster electrons will be at a particular position on the strike camera slits, and slower electrons, thereby transforming time information into spatial image. We also perform a linearity check of our strike camera across different gain factors to make sure that to get the actual response of the strike camera. And what we did next is the calibration of the CCD camera. I forgot to mention that the strike camera usually works together with a CCD camera for producing images that can be processed. So we need to convert pixels into time. So a Kani edge detection algorithm was used, as you can see, to Can you see? Okay. Yeah, to detect edges, then fitted with a least square method. And then this formula was used to get these particular values for the two facilities per pixel. Another important thing is the point spread function of the strike camera. In order to get the actual bunch length, so there is need to estimate the point spread function, and this was done by taking a snapshot of a point laser, approximating the profile. So we got an estimate of the point spread function, and we ended up convolving the measured bunch length from the point spread function in order to get the the actual bunch length. So at the Novosibirsk free electron laser, a custom Cherenkov radiator was designed purposely for this. And one of the limitations of Cherenkov detectors is time resolution, which depends on the transverse beam size of the beam and also the refractive index. So for this, we use aerogel, and we make sure that before the beam traverses the radiator, like the transverse beam is at its minimum. So you can see this is where the detector was placed across the trajectory of the beam. Then with the help of our optical mirrors, we were able to direct the Cherenkov radiation to the strike camera. And we were able to calculate the internal time resolution of the detector to close to a few picoseconds, which is very, very low compared to the sweep time of the camera, which is around 100 of picoseconds. Some experiments were performed at the lasers. At the first laser, we controlled the beam size by varying the RF phase at the gun and also at the bunching resonator. So what happened is actually when the bunchlet sits very close to the maximum voltage of the RF, the electrons in the bunch gain equal amount of energy, so the energy spread is not that much, so the bunch can be compressed. While otherwise, when it sits far away, the electrons gain different energy. The energy spread is high, and the bunch is being stretched. A similar experiment was performed at the second laser, and here we showed the dependence of the bunch duration on the RF phase. We were able to get an optimal phase within minus 12 degrees of the phase. That's where we got the smallest FWHM, that is the bunch duration. We also observe some shape deformation and splitting. For the operators of the accelerator, there is always this rule of precision. There is always need to be there is always need for synchronization between the RF phase and the bunch length. If not, the bunch can end up being splitted into two or lost at some point. We also went ahead to characterize the timing error from our strike camera. We recorded a timing jitter of about 14.3 picoseconds, which is compared to the signals compared to the signal width measured earlier, which was around 50 picoseconds for the minimal acquired beam size and 150 for the maximum. It is negligible. But point to note is that when you are dealing with femtosecond time scales, there is need to take care of this limitation. So at the time of the experiment, we weren't sure about the actual cause of the timing instability. So we further experiments were planned ahead in order to confirm this. At this, I'm done with the free electron laser. Then for the 4M collider, we measured the internal, the natural energy spread. So as I have mentioned earlier, we took a synchrotron radiation from the bending magnets using mirrors to distract camera. Here is an example of a sliced strike camera image. And this is an example of the beam profile, as you can see. Then for the measurement of the natural energy spread, what we did, we set the beam currents to a minimum of 0.2 milliampere in order to prevent any artificial collective effects like space charges and wake fields. We now varied the current at the gradient wiggler, which is a Robinson wiggler, a multipurpose wiggler. It doesn't only produces synchrotron radiation, but at the same time, it provides damping. So by varying the currents, we were able to calculate the energy spread. So the higher the current, the stronger the magnetic field, and the higher the synchrotron radiation. And eventually the outplay between quantum fluctuations and damping. So the quantum fluctuation tends to take over, thereby elongating the bunch. So we took snapshots, calculated the bunch length, and using this formula, we were able to calculate the energy spread. This is the synchrotron frequency. This is our momentum compaction factor. The last facility is a microtron, which is located at Tomsk Polytechnic University. This is the microtron room. The experiment was performed at the optical beamline. As you can see, this a sapphire radiator was used as a source of Cherenkov radiation. I forgot to mention that for the Novosibirsk free electron laser, the average current was about 1 nanocoulomb, so it is very high. So in order not to risk damage to the aerogel radiator, so we reduced the repetition rate. But sapphire, it has more mechanical durability and a good refractive index, so it was used so that it can have a contact with the beam without any damage. So at this facility, we measured the distances between the micro bunches. At the same time, we also measured the bunch length of a single micro bunch. Snapshots were took we take snapshots with 0.75 nanoseconds time, which is 750 picoseconds, where we were able to capture like 2 bunches. Then for a 1.5 nanosecond sweep time, 4, and for a 3 nanoseconds sweep time, you can clearly see 8 bunches. So as I have said earlier, I was tasked to develop a graphical user interface for real-time measurement of the longitudinal bunch length, and this is the graphical user interface, which was developed using PyQt5. It allowed us to upload an image, open the image, subtract background, apply filters for noise reduction, calculate the WHM, and what have you. Part of this research was already published last year, that is 2024, during the IBIC in Beijing, China. So if you want to get more information about our work, I recommend you to go to this paper. So thank you for your time. I'm ready for any question. Thank you.
Thank you. Are there any questions for the speaker? We have time for maybe one or two questions. Just a quick question. Where are you located now? So
currently, I'm in Nigeria. Yeah, I'm done with my MSc, so I am already back.
That institution is where you got your master's is located in
okay.
Russia?
It was in Novosibirsk, Russia.
Yeah. Okay.
Yeah.
Okay.
Okay.
Any questions on the paper, on the presentation? I think we might have some time because Brian, is Brian Neandro? Are you here? I think the next speaker has not yet arrived. What we do in this case is we try to wait maybe 1 or 2 minutes to see if they're going to arrive. And
okay, I can stop sharing, right?
Yes, you can stop sharing.
Okay.
Professor
thank you.
Radia, are you here? I thought Professor Radia was here earlier. I see that, is it Dr. Teba? You are here?
Yes, I'm here. Good morning.
Good morning. And so it looks like the two speakers before you have not yet arrived.
Okay.
We can offer you the option of starting now, and we just swap positions if they do arrive.
Okay.
Oh, but wait, I guess the speaker immediately before you is here, actually. Radia, is that? Yes. Are you, Radia, are you ready to start your talk? I don't know if they walked, maybe made a quick tea run. So maybe it's just best to keep everything on time. Brian Leandro is the one that is not here. Radia is here. And Teba is here. And is that Ishley? Ishia is here. So while we have, I guess, this one speaker that is not here, maybe we'll just use the time to take a quick break, I guess. So, Radia, you can share your screen and start your talk anytime you're ready. Is Radia still here? Oh my goodness.
Lawrence, when we will start?
We're starting now. I'm looking for the speaker who was here a minute ago. Radia.
Okay.
Radia is here and can share. Oh, yeah, let me confirm that you can share. You can share your screen. That's Radia Baktashi. Radia, are you here? It seems like Radia has disappeared. Teba, are you here?
Yes, I'm here.
Okay. So what we'll do in this situation is swap the order, if that's okay with you.
Okay, I don't have problem. We start?
Okay, you can share your screen and put on your slides.
I think it was suggested to wait until 2, I think, or I don't know if it was 30 minutes, I don't remember, but it's okay if you can start.
Yeah, I think when the speaker is not here, I wait 2 minutes. That's it.
Okay, good.
Okay, so we wait.
No, you can start. If the speaker comes, we'll just switch the time slots because we have to keep the whole thing on schedule. And then I can see your screen. If you go to presentation mode, you can start.
Okay. You can see?
Yes.
Okay. Good morning, everyone. My name is Teba.
We need more volume on your end. You need to maybe
Okay.
get closer to your.
Can you hear me now?
That is much better. Thank you.
Okay. So I am Teba Tinina. I am a PhD student.
You suddenly got much worse.
Sorry?
You suddenly got much worse on the audio. Maybe you need to stay close to your microphone.
I'm close. Okay. And now?
It's good.
Is it better?
Keep the same
Yes,
position.
it's good. It's good.
It's good. Okay. So I am Teba Tinina. I am a PhD student at the Department of Chemistry at University of Science and Technology, Houari Boumediene in Algeria. And today, I will present our work intituled Hierarchical Partial Nickel Sulfide Cobalt Sulfide Nickel Nanowire Composite for High Performance Supercapacitor Electrodes. For this, I will start with introduction and discuss the advantage and limitation of transition metal sulfides and present our material design. After that, we discuss our results and conclusion. The rapid growth of portable devices and renewable energy.
Your audio has gotten really bad. Can you get closer to your microphone?
Okay. The rapid growth of portable devices, electric vehicles, and renewable energy has created a strong need for advanced energy storage systems. Among energy storage devices, the most widely used are batteries and supercapacitors. Batteries exhibit a very good storage capability and with high energy density, but they generally suffer from a limited cycle life. In contrast, supercapacitors offer a long cycle life and the possibility of fast discharge process, but their energy density remains relatively low. Therefore, it's necessary to develop new advanced materials for supercapacitors with high energy density while maintaining good cycling stability and high power performance. Transition metal sulfides are among the most promoted electrode materials because they offer high theoretical capacity, multiple redox couples, which provide rich paradox reaction for charge storage. And they also have a high electrochemical activity and stable composition. However, in practice, they can still suffer from insufficient conductivity and structural degradation during long-term cycling. To overcome these issues, in this work, we combine nickel cobalt sulfide with nickel nanowire backbone, forming a core shell morphology. We employ the hierarchical nickel nanowire as a conductive material, which ensures efficient electron transfer and provides mechanical support. On top of this nanowire, we ground a core shell layers for nickel cobalt sulfide, which acts as the main redox active material. This hierarchical structure offers a large electroactive surface area and short diffusion path for electrolyte ions. But overall, this design aims to achieve a high specific capacity, good rate performance, and excellent cycling stability in supercapacitor applications. And now we present our structural characterization, XRD, SAM EDS, and XPS. For the XRD pattern, we can see clearly the presence of three crystalline phases. And all main diffraction peaks can be indexed to the three phases with no additional entity peaks are observed. This confirms that we have successfully obtained nickel cobalt sulfide shell ground on nickel form, which is consistent with our core shell nanostructure design. And for the same results, the image shows that the nickel and cobalt sulfide shell are uniformly covers the nickel nanowire core, forming a microflower-like structure composed of nanorods. This morphology provides many active sets and open channels, which facilitating ion diffusion. The nickel core acts as a conductive backbone, which improves electron transfer and mechanical stability. For the EDF mapping, we can confirm the uniform distribution of nickel, cobalt, and S, demonstrating the purity and homogeneity of the composite. For the XPS spectrum of our composite, show the presence of carbon, oxygen, sulfide, cobalt, and nickel. For the high resolution spectra of nickel, we can see constant orbit level with satellites indicating the presence of both metallic nickel and Ne. For cobalt, also shows two doublet with satellites corresponding to CO2 glass and CO2 glass. Finally, for the S spectrum, presents six corresponding to NES and COS bonds, which confirming the successful formation of nickel cobalt sulfide shell. And now we present our electrochemical tests. The electrochemical tests were performed in 3 electron systems using lithium hydroxide alcohol electrolyte. And on this slide, for the first cycle inventory, we compare our three materials: the nickel sulfide, cobalt sulfide, the nickel nanowire, and the composite. We can see that the area under the curve for our composite is larger than the others, indicating the excellent pseudo-capacitive performance, superior part weight, and the higher specific capacity for this crucial material. This improvement is due to several factors. Firstly, the synergic effect between sulfide and hierarchical nanowire increases the contact area between the electrode and which facilitating force transfer, and also the Faraday redox reaction of nickel sulfide and cobalt sulfide after incorporating hierarchical nickel nanowire improve electrical conductivity, which enhances overall electrochemical performance. For the second cycling, it presents the 3D curve of our material at different temperatures, from 5 to 100 millivolts. As shown in this figure, we can see two pairs of 6 pairs corresponding to the nickel and cobalt redox couple. This fix indicates a battery-like behavior of the electron. Current density increases with the scan rate, and we can see that the oxidation and reduction fix shift slightly without changing the overall curve shape, which shows low surface polarization and meaning that our electrodes can handle fast and reversible redox reaction even at high scan rates. In general, in an electrode, the total charge storage can come from two main mechanisms: the capacitive process, which is fast and surface-based, and the diffusion control process. This process involves ions moving deeper into the electrode. And we can calculate this by separating this contribution for better understanding how the electrode starts and its other electrochemical behavior. For our material electrode, we can see that the diffusion control process dominates, accounting for 90% of the total arc storage, while the capacitive contribution is only for 9.7%. And for the second figure, we can see how this contribution stands with scan rate. When the scan rate increases, the diffusion contribution slightly decreases, while the capacitive contribution increases. Even at high scan rate, diffusion remains the dominant mechanism, confirming that the core shell electrode exhibits excellent electrochemical performance. The charge curves of our material electrode show two potential plateaus, confirming the Faraday redox reaction in the observed in TV. And the curves are symmetrical and highly reversible, indicating excellent electrochemical properties. For the charge time, is inversely proportional to current density with 1 ampere per gram, which showing the longest discharge due to the sufficient ion diffusion into the active material. And for the cycling stability after 10,000 cycles of charge discharge is 98%, and the synergetic interaction between the nickel ion of the core materials and the cobalt nickel ions of the shell can stabilize the core shell structure of the electrode during the charge discharge test. Conclusion: hierarchical nickel nanowire nickel cobalt sulfide heterostructure was successfully synthesized and fabricated. The strong interfacial coupling ensures excellent conductivity, ion diffusion, and structural stability. The electrode delivers a very specific capacity of 1,893 cobalt coulomb per gram and maintains 98% after 10,000 cycles. Finally, this result confirms the effectiveness of interface engineering in enhancing electrochemical performance, making this material a promising electrode for next generation compact particles. Thank you for your attention.
Thank you. Are there any questions for the speaker? We have time for 1 or 2 questions. So in the interest of time, I think we need to keep moving on to the next speaker. And I wanted to go back and see if Radia is here.
Okay. So I stopped the sharing.
Okay. So Radia still not here. So why don't we move on to Ishi? Are you still here?
Okay. Can you see my slide?
Yes.
Okay, let me start. Thank you very much. I'm Takayuki Ishii from Institute for Planetary Materials, Koyama University. Okay. So today I'd like to talk about water in the Marwite, determined by in-situ volume measurements using multi-chamber high pressure apparatus in combination with synchrotron X-ray diffraction. So it is considered that the water is transported into the deep mantle by subducting plate. Discovery of hydrous ringletide suggests that the water is transported into the mantle transition zone. And however, the water cycle and water distribution in the lower mantle is still unclear yet. Oceanic island basalt, which is originated from the lower mantle, have the much water than the mid-oceanic basalt. So this indicates that the lower mantle can have a water-rich source. However, the also hydrous minerals are main water carrier in the mantle. Thermal stability of hydrous minerals are very limited in the lower mantle conditions below the mantle geosan. Therefore, the water solubility of the nominally anhydrous minerals can play an important role to understand the water cycle in the lower mantle. However, the water solubility of bitumenite and ferropericles, which are the major lower mantle minerals, are very limited. So we need to consider another candidate to understand the water cycling in the lower mantle. The Marwite is the third most abundant mineral in the lower mantle. It was reported that the Marwite can accommodate weight percent levels of water, but its report is not very precise because of the experimental difficulty. So Marwite has a main component of CaSiO3 and cubic perovskite type structure. So because the Marwite is unquenchable to the ambient pressure, it is very difficult to estimate water content of the Marwite by using the precise measurements such as FTIR or SIMS measurement at ambient pressure. So there's one study to estimate water content of the Marwite under high pressure. This figure shows the XRD profile of the Marwite under high pressure and high temperature using the laser heated diamond anvil cell. Starting material was the CaSiO3 plus water. They found that the Marwite is a tetragonal symmetry even under water saturated conditions. They also collected the FTIR spectra under high pressure and finding that there is a broad OH band between 3000 and 3500 Kaiser. So they concluded that these bands are from the Marwite and estimating 0.5 to 1 weight% water in the Marwite. This figure shows the volumes of the Marwite under high pressure. This solid line shows the equation state of the dry Marwite. These plots are the volumes under wet conditions. As you can see here, volumes under wet conditions are generally lower than the dry equation state volume. So recent first principle study reported that calcium hydrogen substitution can reduce volumes of the Marwite. In contrast, silicon hydrogen substitution makes increase of the volume. Therefore, the hydrogen substitution mechanism is probably the calcium and hydrogen substitution. However, the previous experiment by laser heat diamond anvil umbilical is has some problem due to the large experimental uncertainties. So in this study, I used a Kawai type multi-anvil press to synthesize the Mawite under high pressure and high temperature. This device is so-called a large volume press. So this device has some advantages. One is the precise. This device can accommodate much more volume than the diamond umbilical, like more than 1,000 times larger volume. And also, this device can control temperature very precisely using the internal heating. So these advantages allow us to discuss quantitatively about the geoscientific problems. So I re-investigated volume differences under dry and hydrous conditions of for the Mawite using the synchrotron XRD in combination with large volume press. So to precisely and accurately compare the volumes under hydrous and dry conditions, I simultaneously determined compared volumes under dry and hydrous conditions in single experiment. So this slide schematically shows the in-situ X-ray diffraction experiment in multi-anvil press. So white X-ray comes from this way, this direction. And X-ray, collimated X-ray penetrates the sample through the gasket and pressure medium. So we can image the sample by penetrated X-rays using CCD camera. We also collect the diffracted X-rays diffracted by the sample by solid state detector to make a sample XRD profile. So this is an energy dispersed method. Then I move to the result. So this figure shows the cell assembly used in this study. So to compare the volumes under hydrous and dry conditions, I put the dry starting material and wet sample together in the one assembly. So this part is the dry sample, and so inside of this dry sample, I put the wet sample in platinum tube with the diamond single crystals, so that the water will not be escaped from the capsule. This figure shows the result of the volume measurements at the several pressures. Red plot shows the volumes under dry condition. Blue plot shows the volumes under wet conditions. As you can see here, at expected mantle temperatures more than 1000 Kelvin, volumes under dry and hydrous conditions are almost consistent within errors. So this figure shows the volume differences under dry and hydrous conditions. So as you can see here, absolute volume difference is about 0.04 to 0.08%. So this suggests that the volume change is very limited, and they might be the very limited water content. So I try to estimate water content of the mite based on our result. This figure shows the volume change with pressure by the calcium hydrogen substitution reported by the previous first principle studies. So at 20 to 28 GPa, volume reduction is about 0.2 to 0.5% when the water one weight percent water is incorporated into the demo. So using these relations, so first I show you that our volume difference, our obtained volume difference is about 0.02% in average. So using this value and this relationship, I estimated water content of the white to 0.05 to 0.08 weight%. So which is very limited water in the crystal structure. So in addition, the previous study reported that peak splitting of the 200 peaks. This indicates the structure of the dendroid becomes tetragonal symmetry. The first principal calculation also suggests that the tetragonal distortion is necessary to hydrate dendroid. However, our study shows the no such peak splitting. This figure shows the 200 peaks during experiment under wet conditions. This figure shows the 200 peaks under dry conditions in this study. So as you can see here, all peaks are always symmetric and seems no splitting. So this suggests that the dendroid has a cubic structure and suggests that the dendroid has limited water. So using these results, I tried to discuss water storage capacity of lower mantle subducting plate. So subducting plate consists of mainly basaltic crust, harzbargite, and pyrite. So pyrite layer consists of the bridgepanite, ferropellicles, and then marwite. So these three minerals has very limited water content. So pyrite should be very nearly anhydrous. So harzbargite layer also consists of bridgepanite and ferropellicles only. So it also has a very limited water content. In contrast, basaltic crust consists of marwite, calcium ferrite phase, silica phases, and bridgepanite. Would have the much higher water content than other lithologies. So our previous study reported that calcium ferrite phase has very limited water, less than 0.01 weight%. On the other hand, silica phases has a much higher water content, up to 1.1 weight%. So these silica phases can contribute to the high water content in basaltic crust. So therefore, we conclude that the water cycling in the lower mantle is controlled by the crustal material subducted from the surface. Okay, so this is a summary. So thank you very much for your attention.
Thank you very much for a very interesting talk. Can I just look at this slide here about the water transport by silica phases? So you are looking at, go back. I'm sorry. Go back to your last slide.
This one.
Yeah, I'll just sort of try to understand physically what's happening.
Okay.
So you're looking at specifically the water subduction, correct?
Yeah.
And I understand correctly that water subduction means water going down, right?
Yes. Yes.
Okay. I'll make sure. So,
but water should be in the crystal structure of the mineral.
Okay.
As like a OH bond, OH bonding.
Oh, okay.
Not just water in general.
Right. So there's basically hydrates going down.
Yeah.
So then there's a completely different process when you talk about water coming up, which would be in the vapor phase, right?
Oh, yes, yes.
Okay.
So I always working on the solid materials. So water in solid materials, right?
Right.
These are all minerals.
Now, can you do experiments to look at like what are some of the properties of water in some of these these phases and these pressure and temperatures, like one thing I used to always ask, sort of in a biophysics standpoint, is like how many water molecules make a bulk, right?
Molecular water.
Yeah.
Okay. Yeah.
I mean, there's like a situation of 1 or 2 water molecules, but then, you know, what happens when you get 100 or 200 molecules? Are you able to look and see like hydrogen bond hopping? Is that a thing at that temperature and pressure?
Oh, yes, yes, yeah. So yes, we can observe it by the, for example, neutron diffraction.
Oh, right. So you can.
Yeah, we can. Yes.
So there are neutron diffraction. There are neutron beam lines that have these ambles.
Yeah.
In Japan. Okay.
Yeah. Yes, in Japan we can do it.
Is there any evidence for a free electron in any of these phases at this pressure and temperature? So is there like an electron hole in the water anywhere?
Electron, free electron.
Yeah. So like in some systems, in biological systems at least, you can get a free electron in at least intermittently or very quickly, where there's a solvated electron. Maybe the temperature and pressure doesn't. Maybe you would think that would happen.
Yeah, I haven't considered it.
Okay. Are there any other questions for the speaker? Well, I want to thank you for a very nice talk.
Yes, thank you very much.
Actually, we have to do more collaborating with people to understand these diamond amble techniques, because that's really kind of a core beamline technique, right? To be able to, or a beamline property to have some kind of core amble. All right, so I think that is the last speaker for this session.
Please, I have a question.
Oh, go ahead, please.
Hello. I am interested to know how you do the modeling of calcium on silicon oxide. Did you first modeling the silicon oxide and then absorb the calcium ion on that structure?
Sorry, could you?
Please, I want to know how you design your material, how you make it, because I am actually working on the design of a copper sulfide, and then I want to absorb a chromium ion on that. I want to see how the chromium ion is absorbed on that surface, and then I want to know how you did, if you first modeling the silicon oxide and then absorb the calcium on that structure, or how you did it, how you make it.
I still don't understand your question. Sorry. You mean
please, let's go to slide 8.
8? This one?
Yes. Your structure. How the calcium is absorbed, like is top. Yes. Inside that structure.
You mean how we know this place of the calcium here?
Yes.
Yeah, it's basically from the X-ray diffraction analysis.
Okay.
But I think the question
because
is,
I saw that you did some DFT calculation, like DFT calculation. I want to know how to design your structure.
design. So
But I
DFT
think
calculations.
this mineral is a davamite. That's a natural material, right?
Yes, yes.
And so you can look at the X-ray diffraction. So you know that's the structure from the X-ray diffraction. So
Yes,
you're not
yes.
synthetically making that.
Yeah, yes. So using the such structure, previous study investigated the hydrogen position.
Okay.
Okay.
Now with that mineral, you're able to make that into a powder or like a thin film or something?
Yeah, in general powder.
Oh.
Mm.
I don't know if that answers her question, but that's what I had.
No, not exactly, because you are talking about the experimental part, but me, I am talking about the theoretical part, the DFT calculation. Because I saw the reference, DFT calculation, Shim et al., how are you the one who designed the structure like this, or you just reference it? Because I want to understand how they made it.
Yeah, this is from the difference.
Okay. Okay, I will contact you later.
Okay, sorry.
Okay,
Yeah.
Okay.
Let's discuss more later.
All right. So, are there any other questions for the speaker? Then, with none, I think we can close this session, which will close the contributed part of the conference. And we have one last talk from the director, CEO of Diamond Light Source, and that will start in 30 minutes. You should come to that talk to see what the message is for a major light source like Diamond Light Source. Thanks.
Bonjour Bernard, tu vas parler? Ou bien?
Prof, j'ai déjà parlé, j'ai déjà posé ma question.
Est-ce que tu vas parler, Erna?
I think there were references made in the chapter
Hi, good afternoon. Kudo, are you ready to start?
Is it Kuda given now?
Hello,
Let me.
this is Gianluigi Button from Diamond.
Yes.
Okay. Yeah.
Good. Sorry. Good afternoon, boss.
All right. Okay.
Yeah. Good afternoon, everyone, and thank you for joining us for our last session. We've got the CEO of the Diamond Light Source, the premier light source in the United Kingdom. So he's going to give us an overview of the Diamond Light Source. Thank you very much. Prof, I think you can go ahead and share your
Yes,
slides.
I'm going to share it right now and put it in presentation mode. Can you see this? Can you see the presentation?
Yes, we can see the
All right.
presentation.
Okay, because I now I don't see anybody anymore. So, well, thank you very much. Thank you, Kuda, for connecting me with the Light Sources of Africa, and thank you for the organizers to give me the opportunity to present a Diamond Light Source. I'm sure there have been other talks about Diamond before. Hopefully, this is not exactly the same talk, but certainly I try to put some of the latest news about the facility. As Kuda mentioned, I'm the CEO of Diamond. Just give a bit of background. I'm a material scientist and engineer coming from Canada. I was also scientific director before joining Diamond at the Canadian Light Source. So I got exposed to African light sources efforts through Michel Fogge, who's probably involved in the organization of this event as well. He's always been involved in this venue. So I'm going to give a brief overview of the presentation, some general background about Diamond, updates on the facility, but also the science, very briefly, because I look at the program. There's been a lot of science discussed, a detailed example of science, and I don't think you would learn much from a general presentation here, but I do want to show some example, in particular how we use the synchrotron to solve some of the largest or the biggest humanity challenges. Then I will talk about how we got to the funding upgrade, what was the road towards the upgrade project, what is called Diamond 2. And I will show also some updates on this actually upgrade as things stand now as of the last few weeks. Right, so this is an aerial view taken this summer. Diamond, we had a very nice summer, and you could see the facility as it is now with the latest upgraded, say, in the infrastructure, which is the power plant. And I'm very pleased to say that this power plant is actually generating about 5% overall of our electricity consumption at Diamond. So on a very good day, even operating, we can generate up to 30% of our electricity requirements. So this is a good investment in sustainability. So I do want to mention that because the climate in the UK is not great, but I just imagine how it can be in countries where we have more sunshine. And I know the Sesame project is actually just started this project on the solar panel, and perhaps I'm not sure what the status of that project it is. What you can see on the background, if you see my cursor, is on the back there is the ISIS. So this is the neutron facility. We have the central laser facility in this region here, and this is really one context about Diamond, that we are located on a beautiful campus with other extraordinary national facilities as well. And that's really something that we value extremely. It just creates an environment that is very constructive for a lot of joint projects and so on. So I do want to mention that. And as you can see perhaps here, on the side, this is again just something. A building is just about to be released to Diamond, which is part of the Diamond 2 upgrade. So I will talk about this later on. So a broad overview. So we are the largest scientific facility to be built in the UK for the last 40 years. We actually are a private company formed as a joint venture between the UK government and the Wellcome Trust charity, which supports 14% of our operating cost. On an annual basis, we have 8,000 users coming and about 14,000 overall distinct users have used the facility since inception. And we have about 800, almost 900 staff on the ground, including the staff that are being working on the Diamond 2 upgrades and also on some grants. What is, in a sense, exceptional perhaps compared to other facilities that we have an output of 50% and 50% for life sciences and physical science. So we have a strong emphasis on the life sciences, very strong structural biology program supporting the user in the UK and around the world. And also strong industrial program. We help companies. We also have about 5% of our revenue or income coming from working with industry. And as I mentioned, we're close to other facilities, including the Rosalind Franklin, which Institute dedicated to life sciences, just across the street. And as I mentioned, we are on the Sarwell campus with a very large number of other organizations, smaller organizations than the national facilities, but that's important to mention. We were built over 3 phases. The first one completed in 2007 with the initial set of beamlines, and then there were additional beamlines in 2012 and 2020. And we're currently working on the major Diamond 2 upgrade. So this is a project. It's not a new facility. It's actually an upgrade of our current facility. And this is how things stand at the moment. We have about 34 to 35 beamline, depending how you count, and also electron microscopes divided in 8 different science groups. Macromolecular crystallography, structured surfaces, magnetic material imaging, microscopy, crystallography, biological cryoimaging, spectroscopy, and soft condensed matter. So that's to list them all. And obviously, we would cover spectroscopy, diffraction, imaging techniques on all these full complement of beamlines. And we also have, it's important to mention, an important electron microscopy effort. We have the Electron Bioimaging Center, which is composed of 5 cryo transmission electron microscope and also the equivalent physical science microscopy facility with 2 aberration corrected microscope and sample preparation and sample checking facilities for those ones. So and in addition, we have sample preparation capabilities for life sciences, protein, crystallization, and also an active materials laboratory. So you can bring samples that are radioactive, and also an optics and fabrication facility, which I'll mention in my presentation. As many other facilities, obviously, we cover a full range of areas of research that have impact in many different areas that I like to say we are there to support and meet the biggest global challenges facing humanities. And these are examples of the area from food sustainability to work in net zero, so what we call the sustainable energy, green energies, engineering, and also work in archaeology and cultural heritage. And we do cover, if you look at the details of the project, we cover 13 of the 17 Sustainable Development Goals of the United Nations. So as with other facilities, we are in a sense, covering large areas of societal impact. More than just the science and publication. So we obviously produce a lot of papers, scientific papers. These are the numbers, also Protein Data Bank. But I think what I want to highlight, our work has been cited in 300 policy documents, so that are from government agencies. You can see example of the agencies. So the World Health Organization, the European Union, the UK government, United Nations Food, etc. So I think this is what is important to highlight, is that we support government priorities and we have an impact not just on the science but also on government priorities. And obviously we work in areas like many other synchrotrons, or all of them probably, areas like COVID, foot and mouth disease, polio, etc. So I think I don't want to list more of that, but I think like many other facilities, I'm sure you heard other talks in this conference talking about the same examples. So I want to show some highlights of the completed capabilities, some recent and some less recent. The first one is the multi-layer fabrication facility, which is part of the optics and metrology group. This is a dedicated facility where we can build optical components, in particular do coatings for optical components like mirrors and monochromators. So we can take object up to a meter in length, which is very impressive. And we can develop our niche optical devices to go beyond what is available commercially. And then this is a picture of that facility. You can see the scale. So the total length is about 9 meters, and you can run a mirror inside that is about 1 meter in length. This is quite impressive. So using plasma deposition techniques. Another one part of this optics and metrology group is the ion beam figuring. So this is really what is called deterministic polishing. So you have an ion beam that can be used to polish surfaces in a very controlled way. So you can generate extremely flat optical components, mirror, for example, that have extremely low roughness. So you can see here the number, just 2 angstrom in RMS variance of the height. So this is absolutely unique by world standards, and we have outstanding results in terms of optical components that we tested in our I-16 test beamlines that are really beyond what is expected from commercial components they can buy. And another component another item that was completed recently, about a bit more than 2 years ago, but I want to highlight it because I will give examples of that in a couple of slides, is the HERF capability, so high energy resolution fluorescent detection, XANE. This is a really designed in-house and built in-house high resolution spectrometer. Looking at that, it would improve significantly the resolution of spectra, which would enhance the detection limits of peaks over the background, so that we would really be able to detect trace elements in very dilute samples. Right. So these are some of the highlights I would like to really emphasize in this presentation. So beyond the beamline, we also have capabilities that help us develop even better capability and also do science that is very competitive. So I'll pick a few examples. First one is related to energy sustainability, so energy production, green hydrogen production. And this is where the work done with the higher energy resolution fluorescent detection on the I-20 beamline was used for. So looking at very tiny shift, looking at concentration of elements like cobalt and ion, and detecting small changes in the valence state of this transition metal. This is what this HERFT capability can be used for, looking at very tiny shifts. And because you have improved energy resolution, then you can detect smaller changes in the spectra. This is correlative work that was done with X-ray absorption spectroscopy, electron microscopy, and also atom probe tomography. So this is one example. The other one again is related to the green energy green hydrogen production, which is also related to more sustainable sources of energy, production of energy, transformation of energy that then can be used in cleaner power generation. So again, this is another set of beamlines, the BO7 beamline that is a XPS beamline that was used to, again, detect the changes in the valence states or the ruthenium atoms to understand the effect of catalysis and the improvement in catalysis for this particular type of catalyst. And finally, another one example in the area of physical sciences. I want to mention this because it's really related to work, and this time on biomass conversion, which is an area of great interest. Here again, X-ray absorption spectroscopy was used on the I-20 beamline, so the same as where I talked about the HERF capabilities in catalyst. And we try to detect the valence state of atoms that are inserted in these mesoporous material with better detection limits. In the area of life sciences, I do want to pick two examples. The first one is related to the use of the IO4 beamline, IO41 beamline, which is the fragment screening beamline that was used extensively during the early days of COVID to try to develop therapeutics to basically try to solve health problems. In addition to the work that was developed, put towards developing vaccines. So therapeutics would be another way to tackle this virus. And the Diamond team worked with universities, not just in the UK, but around the world to develop this fragment screening capability to identify target molecules that would prevent the virus to actually replicating. So essentially, be finding the target sites where we can stop the replication or the function of the virus itself. This is a big effort, which has led to a new project in the area of drug discovery, which is an AI-driven project, which is called now OpenBind. And I don't have time to talk about this, but this is a very recent project that stems from the early days of this COVID moonshot initiative, which was very successful. And then another final example in life science is really the use of cryo-electron microscopy to study cell biology. These are examples of the work trying to understand, detect the chromatin fibers within in cells. And this was developed through the use of the EBIC facility, so the Electron Bioimaging Center, which is operated as a national facility as well, through the use of the regular programs of beamline access. So we use the same user office, we use the same transfer sample capabilities from the users to Diamond, etc. So this is a second example of the science in life in the area of life sciences. And then a last example, touching now cultural heritage, which is something that we've done over about almost 6 years, is the work done in the area try to understand the papyrus scrolls that were discovered a couple of centuries ago, following the Vesuvius eruption that covered Herculaneum in Pompeii. And in about 1850, there was a discovery of these pieces of carbonized papyrus And there was a global challenge to try to decipher and extract the written information within this papyrus structure without actually opening them, because you could imagine you try to open them and everything would be destroyed. So what was done is embed these papyrus scrolls into a 3D printed object, do three-dimensional imaging with the I-12 beamline, try to unwrap this information through digital means. So you have a three-dimensional object, you unwrap the object, and then you try to discover what is written. So it's really spectacular type of work using a combination of physical sciences, AI, machine learning, and an international effort where people actually worked to try to decipher these initially, and then there's work done in machine learning to do this in a more automated way and try to understand what was written on these scrolls. Right, and finally, I want to talk about the Diamond 2 project. This is obviously we do a lot of good science at Diamond, but we know we need to remain competitive by at the international level. And we all know that there have been already a few facilities, including Sirius, Max 4, the Advanced Photon Source in Chicago, that are going through upgrades. And Diamond, already 10 years ago, started the development of the Diamond 2 project, which would enable Diamond to have a brighter source, more coherence, and also greater speed of analysis. So there was and this project was developed over 4 themes: a new machine, so a new storage ring, developing new beamlines, developing new infrastructure, the Diamond Extension building to house some more developments that would be needed for the upgrade, and then also revamp completely the data and the computational aspect. And all these would enable new science, so faster analysis, new capabilities, in terms of scientific term, understanding processes in a more dynamic way, and also using new imaging techniques for developing new imaging technique with better resolution and more better time resolution. So for this, we received funding of about 518 million, which is not just all new money. There's new money from the government and the Wellcome Trust, but also there's what we call business as usual funding. So we need to contribute to the funding of this large upgrade project. And this proposal was developed through the engagement with the user community. We had several workshops. There was working groups, and they developed the science case, the conceptual design report, and the detailed technical design report, which led to the funding of the facility of this new upgrade. So you can see this started 10 years ago. There was a lot of work done by various committees, a lot of work done obviously internally at Diamond to come up with a detailed plan. And this was approved by the Diamond board, and we started seeking funding in 2021, and the application was successful in July 2023, and I was fortunate to arrive just after that in October 2023. So the project is now in progress. These are some of the elements of the upgrade of the facility. We go from this type of cell structure to a much more compact, more magnets, smaller magnets, more magnets. And the idea was the scientific case was to lower the emittance through these better optical components, accelerator components, increase the capacity, so have more beamlines, and also going to high energy, even if it had compromise with the emittance. The scientific case was focused really on the science we could do and the necessary changes in the upgrade. So we improved the emittance by a factor of 20. So give an idea, this diagram gives an idea, it may be complicated, but essentially we have a plot here in terms of the gain factor for the energies, at particular energies, and these horizontal lines here are all the beam lines. We have a diamond, and you can see they're skewed towards higher energies. So the red curve and the green curve are the two designs, one at 3.5 GeV, which is the new design we adopted, which would improve the gain by about a factor about 70 to 100. And then the improvement if we remain at 3.0 GeV. So you can see there's a compromise in terms of the emittance. It's not as low emittance, but certainly there are advantages in the science we could do going to higher energies. So these are the factors at different energy, more specifically using this table. Right, for those who are technically inclined, I provide here the specifications, so the type of the change in terms of the physical structure. So you can see here the energy changes, the current remains pretty much the same, the emittance. You can see the size, the length of the straight sections, and the number of magnets as well. So this gives an overview of the facility. So we have about 40, we would go to from 24 to 48 straights. That gives us additional beamline capacity. So the model structure is based on the ESRF upgrade, and we call this the modified hybrid 6-band achromat. And I'm sorry, I cannot give you the details of what that is implied, but for those of you who are interested, this is the information. So this would improve the brightness. So if you look at the current brightness for the current facilitated lines in blue, and then the improvements given a particular set of undulators for the 3.5 GeV and the 3 GeV, you can see the significant improvement is in particular at high energies. That's where the change is significant. And also in the coherent fraction, you can see the larger change is where obviously the coherence is lower, which is a high energy. So it gives a boost in coherence by about an order, well, a couple of orders of magnitude almost. Right, so that's the improvement. Obviously, it's still the science we do. It's not just about the coherence. It's not just about brightness in the type of experience we can do. So as I mentioned, we have more capacity. So we would have 3 new beam lines. They're listed here. I don't have the time to discuss them. Maybe another time I can talk about more details of these 3 flagship beam lines. 2 of them are in the area of physical sciences. One is in the area of structural biology. So the SWIFT one is really related to operando spectroscopy. So in situ experiments at faster time scales. The coherent soft X-ray imaging is really for imaging techniques, maximizing the impact of the coherence, and then a very high throughput structural biology beamline. And then we would have upgrades to 4 beam lines that will be converted from bending magnets to insertion devices, and then some bend magnet beam lines that would need extensive changes because of the changes in the lattice. And then many beamline would need to be slightly adjusted, either to take the heat from the brighter beam or just slight changes in the position of the beamline, but trying to minimize the changes in the current structure of the beamlines. Right, these are a couple of slides on where we are. The diamond extension building is it's practically complete. We just need some paperwork for us to be able to go into the building and start taking possession and start moving equipment. Essentially, these are essentially needed for the upgrade. So where we're going to assemble the components of the new storage ring. So we would do the bakeouts, we will assemble the beam lines, and do the assembly of the magnets. So this needs to have a controlled, very clean environment. And we already have made good progress in 3 of the hutches for the beam line. So that you can see on the top left, the KO4, so the structural biology beam line, and on the right, you can see the physical science operando beamline. So that's the hutches are practically complete, and there's another hutch which is also in progress. So and finally, this is where we are in terms of the timelines. So we are in November 2025. The key date here is the start of the dark period. So we would switch off the current machine, disassemble it. So this would be starting in December 2027. This is where our users would need to go somewhere else, and this is important to keep in mind. So we're trying to work out if we can provide any help on accessing other facilities. We're working with ESRF at the moment. And then we come back for the users in commissioning essentially at the end, well, in June 2029, so 18 months. And then the first users would be in January 2030. So the first beamlines would be hopefully become operational before that. But certainly we're cautious at this time. This is the current timelines, and we hopefully to be able to stick to the plan. And you can see at the bottom, on the bottom left, a picture of the diamond extension building, which is pretty much ready. We're just waiting for to move in. Okay, so you can see some pictures, and these are on top here, some models of the girders, the prototypes, to actually see how things would be assembled all together, how we can do the maintenance, and what are the potential problems in assembling these components. So it's always good to be able to build something physical rather than just being on a computer, so that you can start putting your hands and see where the problems are. Okay. On that, I think that's the last slide. So essentially, we still are doing great science at Diamond. We have a lot of publication per year. We generate a lot of impact. The Diamond 2 upgrade project is moving forward. We are making good progress on that, and we want to maintain Diamond competitive. So that's where we are now. So I thank you for your attention, and I don't know if there's time for question. I think I used all my time, but hopefully there's a bit of time for more. Okay, so I'll finish there and stop sharing my screen, I think.
Thank you very much, Professor Gianluigi. So I'm just wondering if anyone has got questions. I see.
Thank you.
Yes,
you can go ahead.
Right. So I wanted to ask a couple of questions about the upgrade period.
Yes.
While you're doing that, what are some of the opportunities for, let's say, Africans to get a look into the process of upgrading and building a new facility, which could actually start now, or some of the opportunities for Diamond personnel to fan out across Africa and
talk about well, I can tell you my experience. So when I was at the Canadian Light Source, I visited Diamond in December 2019 during the development of the project. And I felt Diamond staff were very, very helpful because in Canada, we wanted to develop what used to be called the CLS2 project.
Yeah.
So I remember coming to visit Diamond. I spent a day here, and I had the chance to talk to Diamond staff to talk about their experience, what they were doing, were the efforts, what the scale of the engineering that was required at the time. And so these are the kind of things that we happy to share if you want to come and visit. I know we did it also recently with colleagues also at the Canadian Light Source. They were developing the case for various scenarios of upgrades, and they visited Diamond to talk to engineers. That was, we did that. So there's no problem for that. So that's opportunities that you can take anytime. And during the period, yes, there could be opportunities to connect with some people at Diamond. I know Professor Chris Nicklin is connected to Light Sources of Africa. There's some project he was involved with, and I think there's a proposal going in for a project. I don't remember the details, but there are opportunities even to get funding. I think the idea for this funding call, if I remember correctly, is to expose the light sources community in Africa to what can be done and actually support, I think, travel and so on, right? So we are open to that.
Okay. I don't know, Trevor, did you have a question? I don't know.
All right.
Philip.
Excellent presentation. Yeah, this is Philip. I just want to ask one question. That is, I don't know whether your organization has a plan apart from the mobility grants, because if I could remember, Diamond Light Source is not part of those normally listed on the lamp to come for analyze data at the diamond there. And two, do you have also a plan for African researchers at least for them to learn how to operate the system once in a while? Because our major challenges now is, even if we want to have the secret light facility in Africa, we still lack resources in terms of people that's going to be working there. So do you have anything like that, like exchange something for the researchers in Africa? That's I want to know. Yeah.
I cannot answer that question. I would need to talk with Chris Nicklin. I think he is involved. And I don't know, Kuda, are you involved? Sorry, I need to ask Kuda to comment on
Yes.
that, because you're probably involved more than I am with the project that Chris is developing or is involved in. Do you know more?
Yes.
Okay.
So there is, so Philip, there is funding that has been put aside by the UK Research Institutes, UKRI. And what they are going to do is they are facilitating some researchers. At the moment, I think they're starting with researchers in South Africa, where the money will be put aside so that people can have access to the diamond light source. And so we had a meeting recently where we actually discussed potential projects, and so that we identify which beam lines, and then for each particular beam line, I think then they would have conversations and see if the project is feasible, and then it is taken forward. I think you're also aware that there was a START program that was there, I think, before I joined also Diamond. So there are, I think there are projects, and there is I think the UKRI has had 2 years now where they have given, they've had Africa-UK partnerships for research. So with that funding also, if you identify a project that you'd like to do and you contact someone at Diamond, you can then sort of establish a connection, and then you can apply for that funding. So yeah, I think those are the opportunities that I am aware of at the moment. And of course, there are discussions going forward. I think there have been discussions on whether or not to see if the START program can be done again. Of course, it all relies on the availability of funding in the end. Yeah.
Okay, I hope it answers the question. So.
Okay.
Okay.
I have Mac, why don't you go ahead? It seems like you have a question.
Yeah, I think it was the same question. For example, me, I was trained on synchrotron when I think 10 years ago, but without practice, you lose something. So maybe we have to think about how to keep working on these facilities to don't lose the expertise we developed 10 years ago.
Yeah.
Right.
Yeah.
I wanted to ask about as you do the upgrade, there might be some parts and pieces that might become available, some components, which would not be good for a research facility. We're not talking about sort of the ultimate African light source, but might be suitable for TVET type of settings. So in the skilled trade schools for your electricians and
Okay. Well, we actually are talking in particular at the moment with Sesame to see what we could donate. We have some components already that we will announce actually later this week that we will donate to Sesame, and there are other opportunities. So it's something that we can definitely discuss. I know there's a discussion with Sesame. I think if there is a community, the African light source community who sees opportunities, I think it would be good to let us know, because we'd rather see these components to go to a good home rather than being just used for scrap, right? Which is probably, if we don't make an effort, it's just going to be used for scrap parts, metals, right? So we don't want that. But what we need to be mindful is that we don't want to give away any components without thinking what the impact would be. For example, if we give a component that might be good for a school for training, and this component actually would save a synchrotron like Sesame to develop a capability of getting the funding, where we want to prioritize, right? So that actually it's going to be used more effectively. But this is something we are looking at the moment. So if there are particular ideas, I think it's better to know sooner rather than later. But I want to alert you that we are thinking about that. Sesame is an example. And we started, well, we have an announcement we will make actually Friday this week, where we have representative of Sesame coming to Diamond, where we have an official event to mark this donation, and there will be more components later. So we have to be aware of what, where's the best benefit for this kind of instruments that will not be used.
Right. I think what we need on our end is a catalog of what the components are and I guess the condition in which they are in. So probably on your end, you have a good handle. You of course have a good handle on what materials you have, but I don't know to what extent did the 40, 50 some odd directors talk in terms of what do facilities need. So it's almost like there needs to be some kind of a shopping cart or catalog of components. And I mean, just in my opinion, I think Africa would only be interested in components that are in like for trade school type, because by the time we're talking about building an African light source, even components you buy today will be midlife to dead by the time.
Yeah, that's right. Yeah.
So
okay, well, that's good to know that this is an option even for trade schools. I mean, if some of you have worked in synchrotrons, you would know what type of equipment they would be available. So it's mostly would be accelerator components, but I think the beamlines we're trying to reuse as much as possible, so they would be limited, right? So the end station, it would be more problematic because we wouldn't scrap those.
Right.
But there could be optical components like mirrors and monochromators that would become available, or even controls, right?
Yeah.
I think electronics and so on. So that's probably there will be a lot of that. Okay, it's good to know. Yeah.
Okay. Maybe related to that, I don't know if I'll say the last thing, but related to that is I will follow up on this, but how does Diamond get its skilled trade employees? So we at this level, we always talk about the scientists, but what about the electrician and the...
We have to develop them. Yeah, we have internships, so apprentices. Essentially, they come from school. They spend. We have. I think they have to spend. I forget I think it's 4 years
Mm-hmm.
training. They rotate around the facility in different areas. Yeah, so we hire 4 to 6 a year, which is not a lot, but we have limited capacity for that because it's easier to develop that talent rather than just recruiting because it's also recruiting very specialized people. It's much more expensive. So there's a economical factor there. And there isn't a synchrotron schools where you can get people trained. So we know we have to develop anyway. So we have a lot of apprentices overall. So if you think it takes 4 years, so we have about 20 apprentices roughly across Diamond. And also STFC, which is the Science Technology Facility Research Council. They train hundreds of apprentices every year, right? So because they know that they need to recruit from a pool that is not trained, otherwise it's impossible. Yeah.
Right, I understand.
So it's a good question. Yeah.
Okay, I don't know if there's any additional questions. Kuda, do you or Philip?
Yeah, thank you very much. I think we really enjoy the talk, and then we hope that African License will try to think as well concerning those things. And get back to you. But I live with Sesame. I think we are okay because we are trying to have a African beamline at Sesame. Yeah.
Yes.
So I think we are trying to have that. So
Yeah.
I think,
And it could be maybe that the best option is actually is providing. Well, I'm going to meet next week with Andrea Lausi and the machine director and the director of Sesame. That's something I think I could talk to them and see what are the needs, and perhaps even the components we're giving now might be used for an African lights or beamline, right? So I will definitely talk to them about this. That we had I presented this and this was suggested, right?
Okay.
okay. All right.
Okay. Thank you.
Thank
Okay.
you.
Thank you very much.
Okay. Okay. Bye-bye.
Bye-bye.
Bye.
Bye-bye.
Bye.
Yeah.
So I think this concludes our conference for this year.
Yeah. Yeah. So
I want to thank everyone for coming.
yeah, is Prof. Wage there? Prof. Wage? Okay. All right. I think I might need to conclude then because I thought he's there. I sent him a text message concerning the final from the AfPS. Okay. All right. I think we now. Okay. Yeah. Prof. Yeah. Over to you. Yeah.
I am here.
All right. You can give your close remark before I talk. Yeah.
So I would like to thank everybody for coming. This is a wonderful session. I enjoy the talk on diamonds. This is extremely important, and we see that synchrotron light source can do a lot for the development of science in Africa. So what we have to do now is how to bring the African government to give money for the building of the synchrotron light source in Africa. I think that it is possible if there is a real commitment of African government for that. And this conference, African Light Source, African Physical Society, I think that it brings a lot for our scientific community. There was a very, very important communication, discussion, and we hope that next year in present conference, it will be better again and better. And we thank all the contributors, all the speakers, all the people who take their time to come to this important online conference. Thank you very much.
Thank you. Yeah. I will thank you, everyone. I would like to thank the International Organizing Committee, especially Lawrence, Kuda, and others who work to make this conference a successful. I also like to thank all the speakers, those we tried to hijack in 9 minutes, but despite the fact they were here, and others who turn up, as well as all our sponsors. Though this year is a virtual, next year is is going to be a hybrid at Zimbabwe to 2026. So I would like to thank all of them. So, and everyone, other researchers, the attendee, we all recognize you. Everybody recognize you. And then, like we said, at the end of the day, if you have any other thing, peradventure we might send a survey around so that we can be able to know where to improve other areas. There's always room for improvement. So we appreciate if every one of us will be able to try to fill those surveys so that we can be able to improve on some things. And then as well, if you also want to join the African License, you feel free to send us an email. It's there on the website. We definitely welcome you. If you have any idea or any group that you think that is going to help this body, you are all welcome. So on behalf of the International Organization Committee, I think we hereby declare the conference closed. So thank you very much, and then see you next year or in any other conferences online as well. So I will employ everyone. Maybe if you can open your something and wave your hands to say goodbye. All right. Thank you very much. Bye-bye. Cheers.
Thank you. Thank you.
Yeah,
Thank you, Lord.
congratulations. We look forward to see
Special
you
thank
next
you,
year
Lawrence.
again. Congratulations, organization.
Yes. Okay.
Professor Wage, is there another session for ASFAP this coming up now?
Yes,
Or are they...
it is going on. As it is going on. The session is going on there. Yes, you can go.
All right, maybe. I'm a little tired.
It's going.
Okay. All right, I'll talk to you guys later.
Okay.